תודה רבה, thank you. Actually, I was not ready to speak English, but I'll make it mixed. First, I want to welcome our guest from abroad and from Israel. The Open University, probably you don't know much about it. I didn't know much till 5 months ago when I became the president of the Open University. But it's a big challenge because at one extreme, it's an open university. And the openness is in the heart of this university in the sense of open admission, open to society, open without any restriction. It's very easy to maintain excellence when you have a strict filtering and a selective procedure. But when you are open, to keep the high academic level at the other end, and the excellence is a big challenge. And I very much welcome this event here of having the Israeli Computer Science Theory Day, hosted by the excellent Department of Computer Science at the Open University. Usually, most of our events here are aimed to the open part of the Open University, to society, to other topics, and this is one of the few which emphasize and demonstrate the other extreme of having great academic level, academic leadership, excellence within the Open University. So just to get you a short idea about the challenge of maintaining both sides, and then I will switch into Hebrew because I want to read something and I cannot translate it online. אבל כחלק מההכנה לברכות האלה, אז עשיתי מה שכולנו עושים היום, קצת גוגלינג, ומצאתי באינטרנט את המדריך להשכלה גבוהה, שמתאר מה זה מדעי המחשב למי שמתעניין בהשכלה גבוהה. אז ברשותכם אני אקריא קטע, חשבתי שזה משעשע, שבאמת מיועד למועמדים ללימודים שבדרך כלל הולכים, כפי שאתם יודעים, בעקבות התחושה שהם יודעים מה זה, אבל בדרך כלל עד שנה ג' הם עוד לא יודעים מה הם לומדים ולמה. אז במדריך להשכלה גבוהה כתוב ככה. זה לפי דעתי פורסם בערך לפני שנתיים. למרות התפוצצותה הרועשת של בועת ההייטק, לימודים בחוג למדעי המחשב עודם מבוקשים מאוד על ידי הסטודנט הישראלי. הדבר החשוב ביותר שעליכם להבין לפני שתרשמו ללימודים בתחום מדעי המחשב, הוא שתחום זה, כשמו כן, הוא מדע, ליתר דיוק מתמטיקה. התיאוריה העומדת בבסיס מדעי המחשב היא תיאוריה מתמטית, וזוהי גם הסיבה שחוגי לימוד רבים, במיוחד באוניברסיטאות, אינם נקראים החוג למדעי המחשב, אלא אלא החוג למתמטיקה ומדעי המחשב. אנא שמרו עובדה זו בזיכרונכם, בזמן שאתם קוראים פרק זה. אחת התלונות הנפוצות ביותר ששמענו מסטודנטים למדעי המחשב בכל מוסדות הלימוד הייתה שהלימודים אינם פרקטיים דיים, שלומדים יותר מדי מתמטיקה, שהם מרגישים כי אין די דגש על הפן המקצועי, במילים אחרות לא לזאת הם ציפו. באופן כללי, מטרת הלימודים בחוג למדעי המחשב איננה ללמד את הסטודנטים שפות תכנות, המטרה היא לספק להם כלים תיאורטיים שיאפשרו הבנה מעמיקה של עולם המחשבים ושיתנו להם יכולת להתעדכן בעצמם בשינויים המהירים בתחום זה. אז אני חושבת שבאמת האתגר הגדול בכלל בהשכלה גבוהה, ובעיקר בתחומים כאלה, זה באמת להתאים בין הציפיות של מי שבא למציאות. הקטע הזה שבאמת מסביר לסטודנטים שמדעי המחשב זה לא ללמוד שפת תכנות, או אם אני אצטט, ותכף נעשה כאן קוויז מי יודע של מי הציטוט הזה, אחד מגדולי מדעי המחשב שאמר בזמנו שמדעי המחשב אינם עוסקים במחשב יותר משהאסטרונומיה עוסקת בטלסקופ. מי אמר? טוב, עברתם את הבחינה, אפשר לעבור לשלב הבא. אז התיאוריה, או יום התיאוריה של מדעי המחשב, וההרצאות שיש בו, ואני מוכרחה להגיד באופן אישי, זה אחד מימי העיון העיקריים שבהם אני יכולה למצוא כאן באוניברסיטה הפתוחה דברים שברמה האקדמית והמקצועית ידברו אליי, אני אשתדל לדגום אותו ככל שאפשר, ובקצב נייקוויסט לפחות. אני מאחלת לכולכם יום נעים, ואני מקווה שיהיה לכם זמן גם ליהנות מהסביבה הפתוחה שהאוניברסיטה הפתוחה מציעה לכם. תודה רבה ובהצלחה. Thank you.
בוקר טוב. Good morning. Welcome to the second Israel Computer Science Theory Day at the Open University. Israel has a strong community in the theory of computer science, and Israeli researchers appear regularly in all leading international conferences in the theory of CS. We thought that it would be a good idea to hold annual meetings in the theory of CS in Israel. This thought led to the first Israel CS Theory Day that took place here last year. It was a very interesting and enjoyable day, thanks to the invited speakers, Nati Lineal, who is here, Uri Feger, also here, Muli Safra, Yuval Rabani, Alex Mordinsky, Ran Raz, Asaf Naor, and Eva Tardosh. And thanks to the audience that attended this day. This room was filled with about 150 people, undergraduate students, graduate students, CS graduates, and faculty from all over the country. This is the second day, and we hope that it will be at least as successful as the previous day. I would like to thank the speakers who will give a talk here today. We have Ronit Rubinfeld, Noga Alon, Noam Nissan, Sefi Naor, Amir Shpilka, and Salil Vadan, who came from afar to join us. I would like to thank Chagit Messer Yaron and Ora Limor, the president and the former vice president of the Open University, for supporting this day. At this occasion, I would like to congratulate our new vice president, starting from yesterday, Judith Galezer, who is from our department, and I hope that together we shall meet here in the third, fourth, and N+1 CS Theory Days. Special thanks to people who helped organize this day, Daphne Greenboim, Ninette Halfon, Michael Landberg, and Daniel Reichman. Where's Danny? Who orchestrated this entire operation. Thank you. And I will conclude with a few words about our department. Chagit spoke a bit about the university. So a few words about our CS department at the Open University. Some of you may know us, but there are some students here, but some may be less familiar. So we are a distant learning university, and we currently offer a bachelor degree and a master degree in computer science. The method of study here is different from traditional universities, but the curriculum and the graduate requirements are similar. Each course is based on a textbook which is carefully selected from among the texts which are used in the other universities in Israel and leading universities abroad. And then once we have selected a book, this process is peer reviewed. We write a special guide in Hebrew that accompanies the student when he or she studies from that book. On top of those written materials, we have also face-to-face tutorials that take place in various places around the country. And this way, together with a website and other electronic means of distant learning, students are accompanied until they complete the course successfully, I hope. Up until 2003, we were quite a small department. We had only 5 members in the senior faculty staff and around 30 people in the teaching academic staff. And since then, we grew a little bit to now we have 11 people in the senior faculty staff. Still modest, but definitely a 2-digit number, so that's good. And that's it. Let's start. And I hope that all of us will enjoy this day and we will learn new things. Thank you.
Okay, so I guess that in this crowd, I don't have to convince you that distributions are everywhere. We, our colleagues, and even a lot of other people are constantly trying to understand what. So I think distributions are everywhere is something we can all agree on. And in fact, many of us, our colleagues and lots of other people, are constantly trying to understand what sorts of properties these various unknown distributions might have. And what sorts of properties might be interested in? Well, if you want to play the lottery, you might be interested in knowing a couple of things. Maybe you'd want to know, are the samples really coming from the uniform distribution? This could be good and it could be bad. For example, my student Krzysztof, who's in here somewhere, pointed me to a story from Poland where there was a lottery that gave some of the balls had more probability than others, and when people figured this out, they made a lot of money. So it's actually sometimes good to know that your lottery is not uniformly distributed. But you might also want to know, are the draws independent? If you're interested in looking at people's shopping patterns, you might want to see whether sort of shopping patterns are independent of zip code. You might want to compare transactions of 20 to 30-year-olds, 30 to 40-year-olds, and see is there some sort of a trend change, or in other words, are these distributions the same, or are they far apart, say in something like L1 distance? You might want to ask about similar properties about disease data, but you might also be interested in the shape of the distribution. You may want to know, are the diseases more prevalent near big airports? Okay? Or is it monotone decreasing with distance from the airport? Another property of distributions that people really care about is entropy. For example, these people were interested in the entropy of a signal because it told them which neurons respond to which stimuli. So what they did is they apply the stimuli to the neuron. They get some kind of signal that looks like that. Okay? And then they do this many times, and they take the entropy of the description of this signal. Okay? And that gave them some idea of whether the neuron was responding to the stimuli or whether it was just background noise. Okay? So that was another place where you might be interested in distributions is if you have huge data where you don't have time to look at all the data, you just have time to sample it, but you want to have some idea of how compressible is this data. So how compressible in general is undecidable, but how compressible via, say, Huffman codes would be just estimating the entropy from samples of the data. Estimating how compressible it is via Lempel-Ziv is essentially the problem of figuring out how many distinct items you have in your data. So there are also distribution questions hiding in there. Okay, so in all of these examples, what we're interested in this talk is global properties. I don't have a formal definition of a global property, but essentially these are properties that are robust under small changes in L1 distance of your distribution. Okay, so for example, I take my distribution and I say it's close to uniform, and then I slightly change my distribution in L1 distance. It's still close to uniform. Okay, it's a little bit less close, but it's still close. So what's not a global property is I'm not interested in properties of, say, just a few of the elements. Like I'm not going to be interested today in properties that ask whether there is an element of weight at least 1 over square root n or something like that, because it's just a small local part of the distribution, and it changes a lot when you change the L1 distance. Okay, in all of these cases, we're going to assume today that all you have access to are samples of the distribution. You do not know anything else about the distribution, and we're also focusing on the case of large domains. Okay, so in all of these examples we had before, there are lots of different types of answers, outcomes from the probability distribution. And the reason is that basically the standard techniques are just fine for small domains. Okay? But we're interested in large domains because for large domains, most of the techniques require a linear number of samples in the size of the domain. And what we're interested in is if you can find techniques with sample complexity that's sublinear in the size of the domain. Okay? And this is a place where you cannot use the standard statistical techniques like chi-square tests or learning the distributions and arguing about using Chernoff bounds or Hufting bounds that you have a good approximation of your distribution. So you need something else. Okay? Here's our model. We're assuming the distribution is given by a black box. It's a purple box here. The distribution we're assuming is over a discrete domain. The domain size we're going to denote by little n. Okay? And let's just assume for now that the elements are labeled 1 through little n. And this box generates IID samples. Every time you push a button, you get a new sample. We're going to use p sub I to denote the probability that p outputs I. But these p sub I, let me stress, we don't know these. This is just what we're going to use to denote it in the talk. But we don't actually know the p sub I. And of course, we're interested in the sample complexity in terms of n, little n, the domain size. Okay, so let me just give a brief overview of some some things that are known, and then later I'll focus on shape properties. The first kind of question that you might ask about a distribution is whether it's the uniform distribution. And it turns out that the sample complexity of distinguishing uniform distributions from those distributions that are far in L1 distance, epsilon far in L1 distance, is theta of root n. Okay? So you need root n samples to distinguish uniform from far from uniform. And just occurred to me that I haven't defined L1 distance, so let me just define that for a second. So the L1 distance between P and Q is summation of the absolute value of P sub I minus Q sub I. Okay, so we're just summing all those little differences. So testing uniform distribution from far from uniform distribution is theta of root n. Okay, it's very interesting. Okay. All right, I'm going to say a few words about how to do this because that turns out to be a very important problem even for the rest of this talk. So the one way to do this, and this is actually not the best way to do it, but it's the way I'm going to talk about in this talk, is to just estimate the collision probability of your distribution and make sure that it looks right. Okay, what does look right mean? Uniform distribution should have collision probability 1 over n. So if this distribution that's in your black box has collision probability that's much greater than 1 over n, then it shouldn't be close to uniform. Okay? So we're going to estimate the collision probability, make sure it's something like 1 over n. And the other thing we need to do is bound the infinity norm, which means that's just the make sure that there are no elements whose probability is more than, it turns out to be 1 in square root n. Okay, so we're going to make sure there's no really heavy elements that occurs too often. Okay, because that should not happen in the uniform distribution. So that's the whole test. The only difficulty is the collision probability of the uniform distribution is 1 over n, so do you need linear and n samples to estimate that thing well? Like, to see if the collision probability really is 1 in n, you might think, oh my, you need linear and n many samples to estimate this very well. But it turns out, Goldreich and Rahn noted that actually, if you take k samples, you have k choose 2 pairs. Okay, and you can use all k choose 2 pairs to get a good estimate of your collision probability. And even though those k choose 2 pairs aren't independent from each other, they're independent enough so that they give you a really good estimator of your collision probability. So actually, root n samples gives you a really good sample to within very close to 1 in n of the collision probability. And that's why root n samples is enough. And that actually alone gives you a really good estimate of the L2 distance from uniform. And when you also bound the L infinity norm, you can further make claims about the distance in L1 from uniform. Okay, so this is all you need to do. I should mention that the algorithm I just sort of described from above, essentially the only thing you need to remember here is we're going to estimate uniformity via collisions, pretty much. I should mention there's a different estimator due to Paninsky that gets rid of a log n factor and gets the optimal answer. And he actually looks at a different statistic. He looks at the number of elements that occurred exactly once. But I'm not going to go into that any more than that, just to say that there are other ways to do this. Okay. Also, it's easy to see that uniformity testing requires root n examples. Why is that? Well, let's let distribution Q be generated as follows. Pick a random subset of half the elements, okay? And then let Q be the uniform distribution on that random set of elements. Okay? It's very far from uniform because it's only on half the elements. All right, but how can you tell Q from the uniform distribution just from samples? Well, you start taking samples of Q, and you see these labels of elements, and you can't say anything just by seeing names of elements because you picked Q randomly anyway. So this is going to look just like samples from the uniform distribution for a while. And the only time you're going to see a difference is when you start seeing collisions. In Q, you're going to start seeing collisions sooner than in P. Okay? The only thing you can use to distinguish the two is the collision statistics. Okay, so this is something you can formalize, but that's the essential idea. And because in Q you don't see any collisions until root n samples, that's the first time you can even begin to think about distinguishing Q from uniform. Okay? That can be formalized almost exactly the way I said it. Okay, so easy lower bound. All right, so uniformity testing we can do in theta of n to the 1/2, and we can get nearly the same complexity for testing if P is any other known distribution. So now suppose I have some distribution, let's call it Q again, but it's a different distribution. Q is now some distribution, any arbitrary distribution, but I've written it down. You don't need to take samples from Q. It's written down for you completely. Okay? Then it turns out that you can distinguish the case where P equals Q from the case where P is far from Q, also in O tilde of n to the 1/2 samples. So something like n polylog n. And we call that problem testing identity. Sometimes it's called testing against a known distribution as well. It clearly needs at least as many samples as uniformity. It needs at least root n. But the fact that it needs not much more than uniformity is because that essentially there's a reduction from this testing identity problem to something like logarithmically many testing uniformity problems. Okay? So I'm not going to say any more about that right now, but this uniformity testing problem is a very important tool. Okay, here's a new problem. Here, we're testing whether P and Q are identical from the case where P and Q are far. Now here, Q is not written down for us. All we have is access to samples. So I'm going to take a guess. Take a guess. What do you think is the sample complexity of distinguishing P equals Q from P far from Q? Who thinks root n? You guys are smart. Okay. In fact, it's theta tilde of n to the 2/3. So in fact, for a while, we had this algorithm that worked in n to the 2/3, and we kept trying to improve it. We couldn't understand why we couldn't improve it. And it turned out that there was a lower bound. Okay. So some of us were kind of shocked about this, but we had to move on. Okay, what about approximating the distance between two distributions? I want to say, I know P is not equal to Q. I want to know whether P and Q are close from the case that P and Q are far. I want maybe to separate P and Q have distance at most epsilon, versus the case where P and Q have distance more than 2 epsilon. Or even, I would even settle for this. Let's distinguish the case where P and Q have distance at most epsilon from the case where P and Q have distance 1 minus epsilon. Okay? What do you think? N to the 1/2, N to the 2/3? How about N to the 2/3? Anybody going to vote for that? Oh man, you good? You're good. So in fact, this requires nearly linear samples, which some of us found kind of depressing. But so okay, I guess one note of optimism would be that there is a sort of weak approximation that you still can do in n to the 2/3 time. You can distinguish the case where your two distributions are epsilon over root n close from the case where they're epsilon far. Okay? So there is some kind of weak approximation that still can be done, but it's very weak. Okay? So, and also, I hope that in the rest of this talk I'll mention that sometimes problems can get easier if you make certain sorts of assumptions on your distributions, which hopefully are somewhat reasonable in some cases. Okay, so I'm just going to mention a bunch of other problems that have been looked at: independence, k-wise independence, almost k-wise independence, estimating the entropy and other information in theoretic quantities, estimating the support size. These are all problems that have been looked at. But for the rest of the talk, what I'd like to talk about are testing properties of shape. Okay, so some kind of shape properties of the distribution. Again, I don't have a formal definition of shape, so I'm just going to throw some results out there. And actually, I'm really only going to talk about testing monotonicity, and then I'm going to have another slide about some other possible shapes. So I'm kind of cheating. But then that's going to be one part of the talk. And then for the last part of the talk, I'd like to assume you know something about the shape of the distribution and see how that can maybe help us test other properties of the distribution. Okay, so we're going to test properties of shape, and we're going to mainly talk about monotonicity. Okay, so we'll say that the distribution P is monotone if, okay, so first let's assume there's some kind of ordering on your domain. It can be a total order, or it can only be a partial order on your domain. Let's start with a total order. Just, the integers, 1 through 7, they're all ordered. So we'll say that P is monotone if for all pairs ij in the domain, if I is less than j in the ordering, then P sub I should be less than or equal to P sub j. Okay? If I is not comparable to j in the ordering, then I don't care about the relationship between P sub I and P sub j. But if they are comparable in the ordering, then the probability distribution should respect that. Okay? Why are we interested in monotone distributions? Well, many distributions are either monotone themselves or made up of small numbers of monotone distributions. Like bimodal distributions have an increasing part and then a decreasing part. Okay. Okay, so let's start with monotone distributions over totally ordered domains. And let's think about how we might test monotonicity of a distribution. Okay, so kind of, I don't know what the first idea that comes to your head is, but the first idea that came to my head was this should be easy because we can just like pick ranges I to j and then I prime to j prime, and as long as I is less than I prime and j is less than j prime, well, the average weight here should be less than the average weight here. So I should just check that that's true on my probability distribution, and we're done. Okay? That sounds reasonable. It's like a good first step for a test. But then there's a problem. The problem is, what if you take the uniform distribution on even numbers? That's not monotone. That's very far from monotone. Okay? But that would pass any such test. Okay? That looks just like the uniform distribution if you're just looking at ranges. If you never kind of ask about specific points, it's going to look identical. So you're going to need some kind of test that distinguishes the uniform distribution on even numbers or uniform distribution on random numbers from just the plain uniform distribution. Okay? Because uniform distribution is monotone, but those guys are not monotone. Okay? So that's kind of scary. But in fact, thinking about this more makes you realize that uniformity testing is essential to monotonicity testing. So in fact, you can show that testing monotonicity requires root n samples. Why? Because you can reduce uniformity testing to monotonicity testing. Okay? So let's take a distribution P, and let me define the reversal of P. Okay? So here's P. The reversal of P is, I'm just going to relabel the nth element as element number 1. The n minus first element is going to be element number 2. The n minus, and so on. Okay, so it's just reverse this graph and relabel. And now the claim is P is, so first of all, P is uniform if and only if P and P reversal are both monotone. Okay, that's the only way that can happen, right? Okay, well, in fact, it's also true that P is close to uniform if and only if P and P reversal are close to monotone. Okay, so the if and only if isn't actually the same in both directions, but you kind of lose something by going in the circle, but still, there's a sense in which this is true. So what it means is, if I want to test my distribution for uniformity, what I can do is test that it's monotone, and that its reversal is also monotone, and if that passes, I can then conclude that this was a uniform distribution. Okay? And I can also know that if it wasn't close to uniform, this thing would have failed. Right. So monotonicity testing is essential to uniformity testing, but maybe it's actually harder. Turns out no, because you can also reduce monotonicity testing to many uniformity testing problems. Okay, and let's see how you might do that. Okay, so the idea is we're going to try to approximate our distribution by something I'll call a k-flat distribution. What is a k-flat distribution? We're going to partition the domain into k intervals, and the conditional probability in each interval is going to be uniform. Okay, so that's what I mean by k-flat distribution. It's some kind of it's a very succinct order k size description of a distribution. It's just uniform in different partitions. Okay, how are we going to, and then what we're going to do, if we have a good approximation of our distribution by a k-flat distribution, then we can just check if the k-flat distribution is close to monotone. Okay, and if this was a good approximation of the original distribution, and this guy is close to monotone, then the original distribution has to be close to monotone. Okay? So once I pass a distribution using this schema, I am pretty sure that this thing was close to monotone. So I'm not so worried about passing distributions that are far from monotone. I'm not worried about passing bad distributions. My only worry is, why should good distributions pass this thing? Okay? Why would a monotone distribution be approximable by a k-flat distribution? And for what parameters of k that are reasonable for my algorithm? Okay, so our questions are going to be, can we approximate a monotone distribution by a k-flat distribution for k polylogarithmic in n? And so is it the case that all monotone distributions can be approximated by such k-flat distributions? And secondly, is it the case that we can actually find the distribution in time root n? Okay, how do we find these interval boundaries? Okay, and that's, okay, a final question that you might have is, how would you even check if the k-flat distribution is close to monotone? Okay, so one thing I should point out is this is now not a sample complexity question, it's a time complexity question. In this talk, I'm not worried about time for the most part, but since here we can say something nice about time, I'm going to say something about time. So give me 1 minute to talk about time and complexity. Secondly, remember that k is polylogarithmic. So this is a distribution whose description length is polylogarithmic in n. Okay? So we're solving some kind of problem whose input size is already polylogarithmic. Even if you had an exponential time algorithm to solve this thing, it wouldn't be that bad. But it turns out that you can even solve a linear program on these polylogarithmically many variables and determine whether this k-flat distribution is close to monotone or not. Okay? So that happens to be something that's not a problem. But just the most important thing to emphasize here is at this point you don't need any more samples. Okay, so this is not a sample complexity question. All your samples are coming in trying to find these interval boundaries. Okay, so that's what we're going to focus on now. How do you find the interval boundaries, and how do you show that a k-flat distribution exists for k polylogarithmic in n for every single monotone distribution? Do I have 5 minutes left? Or how much? Oh, half an hour. Okay, great. Fantastic. Time flies. Okay. Okay. So how are we going to... Okay. So I can talk slow now. I have a lot to talk about. What do you think, Abby? He once told me I talk faster than Shafi. Okay, so we'll slow down here. All right. Okay, so how we're going to find this k-flat distribution? The idea of the algorithm is going to be we're going to recursively partition our range into half, always in half. And we're going to stop the recursion in 2 cases. One is when the range we're looking at has such small probability that we just don't care about it. It doesn't add much error to the total result anyway. And that, so we're going to say the probability assigned to the whole range is small. In case you're interested, small in this case means something like epsilon over log cubed n. That it's something smaller than that, something like that, so that all the ranges that add up with this total weight, they don't contribute much to the error. Okay? So that's one reason to stop the recursion. Another reason to stop the recursion would be that you reached a range where the collision probability is small. Okay? How small? So small that it makes it seem like the distribution conditioned on being in this partition is close to uniform. Okay? Okay, so small collision probability means at this point you must be close to uniform. And we're going to estimate this really well. We're going to use root n samples to estimate this so that we can really know that if we stopped here, you were close to uniform. Okay? If at any point in this algorithm, when we're recursively partitioning, we have too many partitions, say more than log cubed n, we're just going to stop and output that this cannot be a monotone distribution. Okay? And we're going to have to prove a key lemma that says that a monotone distribution cannot have too many partitions. So anything we fail, it's good because it wasn't monotone to begin with. Okay, when we're done, we should have k partitions, polylogarithmically many partitions, and this will be our output. We're going to have these partition boundaries, and then it's easy to sample the weights of each partition, so we can output a k-flat distribution that's close to p, okay, for this polylogarithmic k. So that's the plan. What do I need to what I'm going to do now is 2 things. I'm going to give you a couple of examples of what this recursion thing does, okay, including the stopping condition. Sometimes we're going to stop because the probability is too small. Sometimes we're going to stop because the collision probability was small and we actually had a uniform distribution in that flat. And then I'm going to show you an outline of this proof of the key lemma. Why is it that monotone distributions do not have too many partitions in this procedure? Okay, so here's example number 1. Here's a probability distribution which is 1 over 2n for the first half of the elements and 3 over 2n for the second half of the elements. And we start with the full range 1 through n. And okay, so let's check. Why did we stop the recursion? Either because the probability assigned to this was too small, It's not too small because it's all the probability right now, so that's not going to be a reason to stop right now. Or we would stop because the collision probability was really, really low. Now in this case, it's not going to be because this thing is not close to uniform. Okay? So we're going to partition. Okay? And these are the conditional distributions you get on the two partitions. This is 1 through n over 2 and n over 2 through n. Now, should we stop now? Well, neither of them have small probability, so that's not going to be a reason to stop the recursion. But both of them have small collision probability because they're both uniform. Okay? So we stop, that's it. This is what we're going to output. We're going to output actually a 2 flat distribution. It's got 2 partitions of the data, and this is what of the domain, and this is what we're going to output. Okay? Any questions on that one? Okay, now comes the tricky one. What about this distribution where the last element gets probability a half, a quarter, an eighth, and so on? What would we do there? Okay, well, we definitely have bad collision probability, so we're going to partition this node. Okay, and this guy now, he has very small weight. Okay, so we're going to stop. That's just small, so we stop recursing there. On this side, however, we have large weight, and we have large collision probability. So we keep partitioning. Okay? Again, the left has small weight, the right has large weight and bad collision probability, and we keep going. Eventually, however, you start getting, actually it happened here, but this, I didn't use a large enough n for this example, but eventually you get to the point where you start sending some probability weight to the left. Okay? So you might not actually decide that this guy is small at some point. In fact, probably already here I shouldn't have decided it was small because it was this whole weight, right? You can actually see it. So, so you might actually start partitioning on the left as well. Okay? But whatever you do, what you're going to end up with is a subset of a binary tree of height log n. Okay? So let's just think. In the previous example, we split once. We outputted a 2 flat distribution. That tree that we made was of size 3, right? Here we have somewhat bigger partitions, right? And we end up with maybe 2 to the log n many partitions that we output, right? So that's something like logarithmic. Okay, that's good. So let's notice a couple of other things. The depth of this tree is bounded by log n, right? Because we're always cutting in half. So there's no way this depth can be higher than log n. All right, another thing to notice is either we partition into 2 or we stop. Okay, so it's actually a full tree, right? Both kids are there or no kids are there. We never have long chains. Okay, so that's another thing just to notice. Okay, because now we're going to prove that for monotone distributions, the number of the partitions has to be log n, log n. And what we're going to show is we're going to look at the tree of the partition procedure. And what we're essentially going to do is use the fact that we know there's at most log n levels. We're going to show that at any level, there's at most log n many nodes. Okay? And that's how we're going to bound the total number of partitions. Okay, so for a given level h, consider these live intervals v1 through vm. These are the ones that haven't been declared too small. These are the ones that are still alive. They're either uniform from kind of from above, or they're still alive, but they have not been declared too small. Well, notice that in these live intervals, okay. All right, so notice that in the live, because we're only proving this claim for monotone distributions, all the probabilities in V1 are smaller than all the probabilities in V2 and so on. Right? So these probabilities are all increasing. Okay, so these probabilities are increasing, but furthermore, they're jumping. Okay? At some point, some of these guys are jumping. So if VI and VI plus 1 were split from the same parent, there had to be a reason for that split. The collision probability was too high. And that means that they weren't close to uniform. If they're not close to uniform, then there has to be a reasonable difference between the smallest element in VI and the largest element in VI plus 1. Okay? So you can actually make this formal proof, a lemma that says that if VI and VI plus 1 were split, there's at least a 1 plus beta factor difference in the probabilities of the extreme elements. Okay? So you're either getting bigger or you're always getting bigger, but sometimes you're actually jumping up in probability weight. Okay? Well, there's not that far you can jump. Okay, so let me also mention that actually at least half of these guys have to be jumps. Okay, because this tree was full, at least half of these internal nodes have to be siblings. Okay, so at least half of 1 through m, half of these guys have to be siblings. So half of these had to be jumps. Okay, and you can't jump that far because you start at something that's at least 1 over log cubed n large, because we got rid of all those really small weight nodes. And a probability can't be bigger than 1. Okay? So how much can you jump? You can only jump log n times. Okay, so you can use this to bound the number of lag intervals per row of that tree. Okay, this, just in case you don't remember, this is the tree I'm talking about. So any row on this tree can have at most log n many nodes on it. Okay? And the depth is only log n. So the total number of nodes is at most log n, log n. Okay, and that's how you show that. All right, so what this gives you is an O tilde of n to the 1/2 over epsilon squared sample complexity bound for distinguishing monotone distributions from distributions that are epsilon far from monotone. Okay, what about general posets, not just totally ordered posets? Here the story gets a little bit more intricate and maybe good because there's lots of open questions. But it turns out that if your poset has nice properties like it's decomposable into a union of W disjoint chains of length at most C, then you can test distributions with O tilde of W root C many samples. Okay. So how do you do that? Well, you approximate each chain of the distribution of the poset by a k-flat distribution, and then you check if the resulting distribution is close to monotone. But now you have to check that things are consistent between chains as well. Okay, but it turns out something that is doable. What's nice about this is that it gives an O tilde of capital N to the 3/2 bound for the capital N by capital N grid, which was actually roughly known before, but this simplifies greatly and is slightly more efficient than a result that was known before. And it also gives a slightly sublinear bound for the hypercube. Okay? So the capital N dimensional hypercube has 2 to the n many nodes, but you can actually test monotonicity in 2 to the n over root capital N. Many samples on the hypercube. So it's sort of a general purpose result. It's possible you can do better on that hypercube, I don't know. It's also possible that you can do better on the capital N by n grid. Okay, now the bad news is there are also posets, actually very simple posets, just the matching, for which monotonicity testing requires nearly linear samples. So that's kind of depressing because previously all these examples of problems where we knew we needed nearly linear samples were these kind of distance approximation problems, and we were kind of hoping that would, we could stop the damage there. But here is a real property testing problem where even that requires nearly linear samples. Okay, so let me just, this is my slide to pretend that there are other properties of shape that I'm interested in. One is cheating because it's unimodal distributions, which is essentially monotone and then anti-monotone part. One might also be interested in clusterable distributions. Is the support of the distribution K clusterable by radius R? So it turns out that that's something that you can say. Something that's actually open, but I would imagine that if anybody thought about it, you could do something about this. Is what about testing whether a distribution is k-flat? Okay, so the techniques I mentioned work only when you start with something monotone. When you're testing so the techniques I mentioned, if you start with a k-flat distribution, may not actually output a k-flat representation. So it's not clear that the techniques I mentioned actually give you anything for testing whether a distribution is representable by a k-flat distribution or not. But what they may be able to do is approximate the best k. Okay, so that's still open. And something that I think people would be interested in is if you could test whether your distribution is a mixture of k-Gaussians, especially if you could do this faster than it takes to actually learn the k-Gaussians. Okay, so there's a lot of literature on learning mixtures of k-Gaussians. But what about testing? And maybe if you could do it sublinear in k, that would be even more amazing. Okay, so now I want to stop talking about testing properties of shape. I want to talk about how you can use the shape of the distribution to help you test other properties. Okay, so here's an example. If you have a distribution that's uniform on any subset of the elements, okay, not necessarily even contiguous subset of the elements, in this case, you can estimate the entropy somewhat faster than you could if you didn't know anything about the distribution. Okay, so that's one example. What if you know that your distribution is monotone? And let's start with totally ordered domains. Okay, if you know your distribution is monotone, how about testing uniformity? Remember before, when you knew nothing about your distribution, we needed root n samples. How many do you need now? Constant. Okay, really 1 over epsilon, but I mean 1 over polynomial in epsilon, but constant in terms of the domain size. That's all you need. Because if you know the distribution is monotone, all you need to do is make sure that the distribution assigns roughly the same amount to the left half of the domain as it does to the right half. Okay, and you can show that the difference in weights it assigns to the two halves of the distribution ties directly into its distance from uniform. Okay, so you can prove that kind of relationship. It's simple algebra, and you're done. Okay, something else you can do when you know your distribution is monotone over a totally ordered domain is with polylogarithmically many samples, you can test closeness, you can test independence, you can estimate the entropy. These are all things that took n to the 1/2, n to the 2/3, n to the 1 over gamma for gamma greater than 1. Many samples when you didn't know anything about the distribution, but now you can do it with polylogarithmically many samples. And the idea, you might actually guess by now, is to use these k-flat partitions to approximate the distributions. But now, since you know it's monotone, you don't have to do that uniformity testing step everywhere. You can just figure out the partition, and you don't have to check the collisions in between. Okay, so you figure out how to partition it with a slightly different criteria, but essentially the same idea. And once you figure out a k-flat approximation of your distribution, you can just test the property on the approximation, and you're done. Okay, so monotone. Knowing that the distribution is monotone helps you an awful lot for testing these properties. Okay, what about partially ordered domains? Can we get the same big wins in that case as well? Okay, well, let's take an example of a partially ordered domain that has high dimension, the most high dimension. Let's take the Boolean cube. Okay, so 0, 1 to the n. This is our biggest point, 1 to the n. That's our lowest point, 0 to the n. And we want to know here, can we get algorithms whose sample complexity is polylogarithmic in the domain size for testing uniformity, testing identity, entropy? And remember here, polylogarithmic in the domain size, which is 2 to the capital N, is the same as saying it's polynomial in capital N. Okay? Okay, so I'm using capital N for the dimension. And it turns out that there's some good news. Testing uniformity can be done in O tilde of capital N, the dimension, over epsilon squared sample complexity. Okay, so for testing uniformity, and how do you do this? Well, to say this, let me define something called the bias. Bias of a domain element x. Okay, this has nothing to do with the probability distribution. It's just the bias of a string x. It's 2 times the number of 1s in x minus capital N. So the top element has bias n. The bottom element has bias minus n. The equator has bias 0. And the bias essentially tells you which level of this hypercube you're on. Okay, that's all it tells you. And just it's normalized to minus n and capital N. Okay, so notice that for the uniform distribution, if the expectation over x chosen from the uniform distribution of the bias of x, in other words, the average bias of x, is just 0. Okay, that's pretty easy to see. If P is monotone, it's also fairly straightforward to see that the expected bias is positive. Okay? If it's not the uniform distribution, then it has to be top-heavy. Okay, so it has to be positive. All right, so we're going to use this. Okay, so let's think now. We've defined this thing of bias. The uniform distribution has bias 0. Okay, we know our distribution is monotone, so we know our bias is positive. The only monotone distribution that has bias 0 is the uniform distribution. Okay, so how about to test for uniformity? Okay, we know P is monotone. We're testing for uniformity. how about we do this? Why don't we just estimate the bias and see if it's close to 0? Okay? And that, in fact, is going to be our algorithm. We're going to take a bunch of samples, calculate the average bias, and if the bias is close to 0, let's say less than epsilon over 2, we're going to output uniform. If it's greater than epsilon over 2, then we have significant bias, so then it couldn't have been the uniform distribution, and we'll output not uniform. Okay? So that's going to be the algorithm. And it's pretty clear if this, okay, so I'm showing you actually a first try. So this is more samples than what I originally claimed. This particular algorithm takes capital N squared many samples. But with that many samples, if you plug it into your Hufting bounds, you get a really good estimate of the bias. Okay? And then if you plugged in the uniform, if you took samples from the uniform distribution and you took that many samples of it, you're going to get a good estimate of 0 to within epsilon over 2. Okay, so you really are going to see a number that's less than epsilon over 2. And, okay, so the only question that remains here is, why is it that step 2 catches non-uniform distributions? Okay, why is it that non-uniform distributions are usually going to output far from uniform? So it has to be, what we have to show is that their bias is at least epsilon, that their expected bias is at least epsilon. Okay, so that's what we're going to show next, that their expected bias is at least epsilon. And then, because of the good sampling, like because we took enough samples that we can apply Hufting bounds, we're going to, if our expected bias is at least epsilon, so our estimator is going to be at least epsilon over 2 with high probability. Okay? So that's what we need to do now, is show that the expected bias is at least epsilon in the case that the P was at least epsilon far from uniform. Okay? Now, I'm not going to prove this, but I'm just going to say a few words about the proof. It follows from a canonical path argument, and it can be viewed as a real-valued version of the classic result that any balanced monotone partition of the hypercube into red and blue nodes has to have at least omega 2 to the n bichromatic edges. So it's a sort of influence-type argument. Okay? All right. To give the more efficient version of this result, you just have to slightly modify the algorithm. Let me just go back to this picture. So to slightly modify this algorithm, notice that for the uniform distribution, if you take that many samples, you expect them actually all to be within a root n, square root n band around the midpoint here. Okay, it's very unlikely. Okay, go ahead. Okay, it's very unlikely you'll be way up here or way down here. So they're actually, you expect them all to be here. So why don't we say that if we see anything up here, just reject, this couldn't have been the uniform distribution. Okay? Why does that help? Why it helped is that it changes the value of our, it lowers the variance. Okay, so it gives us a range of O tilde of n to the 1/2 rather than a range of O of capital N. And so we can plug in better numbers into our Hufting bounds, and it gives us a sample complexity of O tilde of n rather than O tilde of n squared. Okay, so that's just how you can improve that algorithm. Okay, so we just saw a positive result. We can test monotone distributions for uniformity using O tilde of the dimension many samples, but unfortunately for all these other problems, things are not so great. Okay, so it turns out that you can show an exponential in the dimension lower bound for testing equivalence to a known distribution, or what I also called testing identity earlier. Okay, so, and the really depressing thing is, it's even for just the simplest possible known distribution, a product distribution. You would think that if you could test uniformity quickly, you should be able to test a product distribution because it's so similar to a uniform distribution. It's independent, every bit is set to 1 with even probability 2/3. Even that, we can't, there's an exponential lower bound. Okay? So that's kind of depressing. And there's also an exponential in the dimension lower bound for approximating entropy. And it turns out that there's a technique that's based on monotone subcube decomposition. You can use these to define a class of distributions to give all these lower bounds. So it's the same technique for all of these. You can also show that this uniformity test is nearly the best possible. So you need some dependence. You need a linear dependence on the dimension, which means that you can't be completely independent of the domain size in this testing problems. Okay, so this is kind of depressing, but it still leaves open the possibility that you can do better knowing that the distribution is monotone than the results we have for when you don't know anything at all about the distribution. So remember there we had, for testing equivalence to a known distribution, we needed root the domain size many samples. That would be 2 to the capital N over 2. Okay? So it may be possible, knowing that the distribution is monotone, to test it with 2 to the capital N over 10 or something like that. Okay? So that's a possibility. Also open is other kinds of partial orders. And I guess at this point, I hope I've convinced you that there are a lot of open problems in this area. There's several useful techniques known. We borrowed from learning theory, from influence of Boolean functions. Some of it is just algebraic calculations. But there's a lot of different directions to go. I think the main open questions are what other properties have sublinear tests for them? And when we have strong lower bounds, are there some kind of reasonable assumptions we can make on the distributions so that we can get better algorithms for them? Another thing that I didn't talk about at all is what about other query models? For example, I assumed here that you could not access probabilities of the distributions. I could not ask what's the probability of element 10. Okay? But actually, it may be reasonable in some cases to assume you have that kind of access. For example, Google, a couple of years ago, made public a bunch of texts it had collected and all the n-gram data. So they did all those calculations for you, and then you spend 2 days downloading this huge data set. But then you have all the texts which you can randomly sample, so you can construct your own little routine that gets a random sample of a text. And you can also query their statistics to see the probability of every single word and also the probability of co-locations of words. So there's a lot of information that they did for you. And you could do yourself if you had a lot of pre-processing time. So I think that this question of other query models can be an interesting one. One just has to find the right setting. And one other one I'll just throw out there is what happens when you can't assume that your samples are IID, but maybe you can assume some other relationship between them. Okay, so that's it.
So I'll be talking about a new computational analog of entropy and applications in cryptography. This is joint work with Iftach Heitner, Omer Reingold, and Hotek Lee. Okay, so I'll start with just a quick review of what we need to know about entropy for the purposes of this talk. Then I will talk about something that's fairly well understood by now, but it'll be useful in setting context for what we do, and that is the relationship between secrecy sort of conditions in cryptography and another computational analog of entropy known as pseudo-entropy. And then I'll talk about other kinds of security conditions in cryptography, unforgeability kind of conditions, and that will lead us to our new notion of inaccessible entropy, and then we'll see spend a little bit of time on applications as time permits. Okay, so what do we need to know about entropy for this talk? So for the most part, we'll be talking about Shannon entropy. So Shannon entropy of random variable, you take the expectation over samples of the random variable of log of the reciprocal of the probability mass. Sorry, the fonts don't come out, so this is a left arrow to indicate sample from the distribution. We won't need to work much in the talk with the formal definition. You can just informally think of this as a measure of the number of bits of randomness in the random variable capital X here on average. So think of this as the randomness in the individual sample, and then we're taking the expectation of that. It ranges can be from 0, and the largest can be as log of the size of the support of the random variable. Here, all logs are base 2. At these two extremes, it has a qualitative meaning. At 0, it just means that X, the random variable, is concentrated on a point, and at the large, it achieves equality on the other extreme, if and only if the random variable is uniform on its support. And so for a lot of the time, we'll just be talking about these two qualitative extremes, but then it'll be useful and important for us to have a more quantitative measure in between. Okay, and then we'll also talk about conditional entropy. You have two jointly distributed random variables, X and Y. The entropy of X given Y, you just take the average over samples of Y of the entropy of X the conditional distribution of X given that sample. This satisfies the nice chain rule that entropy in two random variables, x and y, is entropy in y plus the entropy of x given y. Conditioning can only reduce entropy, so the entropy of x given y is at most the entropy of x. That holds with equality if and only if x and y are independent. And the most that conditioning on y can reduce entropy is by its own entropy. And that holds if and only if y is a function of x. And another extreme, this is also always non-negative and kind of follows from the thing we said before about when Shannon entropy is 0, that the entropy of x given y is 0, and x has no entropy given y, has no entropy left given y, if and only if it's completely determined by y. X is a function of y. Okay, so I mentioned that we should think of Shannon entropy as randomness on average. There are also worst-case notions, analogs of Shannon entropy that we'll refer to but not really work with much in the talk. Min entropy, where you replace the expectation with a minimum. This just means you look at the heaviest element according to the distribution. And then something that's maybe less well known, max entropy, which corresponds to just that upper bound on Shannon entropy we talked about before, just log of the size of the support. So the Shannon entropy is sandwiched between the min entropy and the max entropy. So saying the min entropy is high is a strong way of saying the random variable has a lot of entropy, and saying the support size is small is a strong way of saying it has small entropy. Okay, so now on to talking about what entropy has to do with cryptography. And this really goes all the way back to the sort of classic works of Shannon, who gave the first mathematically rigorous treatment of cryptography and security. And he gave us a very nice definition of, you have an encryption scheme here. Here we're talking about private key encryption. He defined an encryption scheme to have perfect secrecy if for every two messages, m and m prime, say we're encrypting n-bit strings here, the encryption of m has the same distribution as the encryption of m prime. This is not the way he defined it, but it's equivalent to his definition. And here the randomness is coming over the choice of a random key k, capital letters denoting random variables. And this is only capturing security for one application of the encryption. It doesn't talk about when you encrypt many times. This is a very nice, very strong definition, but what Shannon unfortunately showed is it has a severe limitation, that if you want to encrypt n-bit messages, your key must be of length at least n. Okay, and so if you're encrypting many times, your key length has to be as long as the total number of messages, bits that you're encrypting, and so it's not really a practically achievable notion. Okay, so I want to review very quickly Shannon's proof of this using entropy because it will also just help motivate things that come later. Okay, so so imagine now to prove this, we have this encryption scheme. Imagine we encrypt a uniformly random message m. We choose a uniformly random n-bit string and encrypt it, and look at the joint distribution of that message together with this encryption. Well, what perfect secrecy says is that the encryption's distribution is independent, doesn't depend at all. It's the same for all messages. So that means that these two are actually independent of each other. That is, has the same distribution if I chose an independent uniform n-bit string, which I denote by use of n, together with the encryption of m. And as a result, if I look now at the conditional entropy of m given the encryption, it's the same as the conditional entropy of this uniform distribution, which is just n. Right? So just using this qualitative high-end extreme of entropy. On the other hand, the fact that you can decrypt means that if I'm given the encryption of a message and the key, the message is completely determined. So that means that the entropy of m given the encryption, its encryption and the key is 0. And now, since conditioning on the key can reduce entropy by at most the entropy of the key, we get that the entropy of the key is at least, the entropy of m given the encryption is at most the entropy of the key. Right? And so then putting these two together, you have the entropy of the key is at least n, and hence the key must be of length at least n. Okay, so that's Shannon, and the fundamental realization that came in the 70s that enabled bypassing this severe limitation that Shannon showed was the realization that we don't really need perfect security. It suffices for us to have security against feasible adversaries, the ones who run, say, in polynomial time. Taking this sort of computational perspective leads to the following computational analog of Shannon's definition of secrecy, computational secrecy of Goldwasser and Macaulay, where instead of requiring that the encryption of any two messages have the same distribution, we just require that these distributions are computationally indistinguishable. That is, no feasible, say, polynomial time algorithm can distinguish a random sample of one from a random sample of the other, except with negligible probability. And this allows us to have a key length much shorter than the length of the messages we're encrypting. So it may be informative to see where is it that Shannon's proof breaks down. Well, it's here in the first step. So when we have only computational secrecy instead of perfect secrecy, then all we can say is that the message, when we look at the encryption of a random, uniformly random message, is indistinguishable from the uniform distribution given the encryption. And so instead of we can't say that its entropy is n given its encryption, but only that in some sense it looks like it has entropy n given its encryption. All right, so qualitatively we can think of this as saying that the message has pseudo-entropy n given the distribution. Right now I'm just using this informally. In a moment we'll see a more general quantitative definition of pseudo-entropy. All right, and the key point is that it is possible to have distributions whose pseudo-entropy is much larger than their actual entropy. Okay, so for example, if I take the output of a pseudo-random generator on a short k-bit seed, it's the real entropy of its output on a random seed is at most k, the length of the seed, but it's indistinguishable from the uniform distribution. That's the definition of a pseudo-random generator. And so its pseudo-entropy is n. And so if it stretches by a lot, its pseudo-entropy is much larger than its actual entropy. Okay, so what's the more general quantitative notion before going into this quantitative, one more thing I want to point out here is that there's a sort of an asymmetry here between the honest parties and the adversary. So when we talk about secrets here, this is really from the perspective of the adversary. The message looks like it computationally has n bits of entropy given the encryption. But from the honest party's perspective, we're really in the second case, because to the honest parties, they can see that the message doesn't have much entropy given the encryption, because they have the key, and given the key and the encryption, they can compute the message. So this point, this sort of asymmetry will also come up. This kind of asymmetry will come up when we talk about our computational notion of entropy. All right, so now what's a more general quantitative notion of pseudo-entropy? This was given by Hassad and Pagliazzo, Levin, and Luby. They defined a random variable x to have pseudo-entropy at least k if x is computationally indistinguishable from some random variable y whose real entropy is at least k. Okay. One thing to note is I'm only defining this as a kind of lower bound, so I'm saying the pseudo-entropy is at least k, and we'll come back to why I only think this definition is only useful for saying kind of entropy is high. We'll come back to that later. Okay, so this is a nice definition, but what is it good for? Well, it was a key concept in the celebrated result by Hassad et al. That pseudo-random generators can be constructed from any one-way function, that they can be based on the sort of minimal complexity, the minimal assumption for complexity-based cryptography, that you have a function that's easy to compute in the forward direction, but hard to invert. And the way their proof goes, just schematically, is the first step from a one-way function. They show how to build a random variable whose pseudo-entropy is slightly larger than its actual entropy. All right? They construct a random, and in fact, one that you can sample efficiently in polynomial time, random variable x pseudo-entropy that's indistinguishable from some random variable y, whose entropy is bigger than the entropy of x plus some tiny amount, noticeable amount, 1 over a polynomial. Then the next step is they take many repetitions, many independent copies of x, and what this does is it increases the gap from being small, just 1 over a polynomial, to being large, a large additive polynomial gap in bits of entropy. And additionally, it has a nice effect of turning this average case notions of Shannon entropy into the worst case notion. So you actually get x has pseudo-min entropy that's large, and even larger than its max entropy. All right, I'm cheating a little bit here. I'm ignoring some negligible statistical distance that comes in. And then by some hashing, they're able to convert the pseudo-min entropy, right, being indistinguishable from having large min entropy, to being indistinguishable from the uniform distribution, okay? And the fact that it has a small max entropy, small support size, into having a short seed, okay? And that's exactly what you want from a pseudo-random generator. Okay, so that's all nothing new. So now in the rest of the talk, I want to use to talk about a different kind of notion of computational entropy. Okay, so really the starting point is that cryptography is not just about secrecy conditions. And in particular, there are many security conditions in cryptography that have a sort of a different kind of flavor, which we will see is in some sense complementary, which are sometimes referred to as unforgeability conditions, where instead of saying that there's information that's hidden from an adversary, so what secrecy is about, these conditions say that it is hard for the adversary to do something without being caught. In particular, it's hard for an adversary to generate valid-looking messages when it's not supposed to be able to. All right. So examples are unforgeability conditions of digital signature schemes or their private key analog message authentication codes. Here, if someone doesn't possess the signing key, it shouldn't be able to generate messages together with signatures or MACs that are valid, that fool the honest parties into thinking they're valid. Another property is collision resistance of hash functions and binding properties of commitment schemes, and we'll talk about the latter two in some detail later in the talk. Okay, so let's go talk about actually this collision resistance example now. So suppose we have a family of collision resistant hash functions. What does that mean? So it's a family of functions that are shrinking. So that's why they're referred to as hash functions. So say taking n-bit inputs to some n minus k-bit outputs. With the property that if I pick a random function from the family and give it to you, it's infeasible for you to find a collision in the hash function, two inputs that map to the same output. All right, certainly think of k as fairly large, even polynomially related to n. So since f is shrinking by a lot, there are definitely many, many collisions. Yet, if I give you a randomly chosen function from the family, it's hard for you to find one, except with negligible probability. Okay. So now think of a following game or protocol between two parties A and B using this family. Party B picks a random function f from the family. I'll write it by a capital letter just to emphasize that it's a random variable. Sends it to A. All right. Now A picks a random input to the hash function, x, uniformly at random, and then computes y, f of x, and then sends that to B. Okay. And now we're going to do something strange, but you'll see why. Now imagine A sends x to B. Okay, so what I'm interested in looking at is the entropy of x given y and f. Okay, so that's the reason for this strange, seemingly strange, if I'm going to send x, why do I send y at all? It's because I'm going to look at the entropy of x given y and f from two different perspectives. So one perspective is from the perspective of someone just looking at this interaction from the outside, or even from B's perspective. I claim that x has a lot of entropy given y and f. And this is because the hash functions are shrinking. So when I take x, originally it has n bits of entropy. All right, conditioning on F doesn't reduce its entropy at all, because X and F are chosen independently. And now conditioning on Y, I'm conditioning on a string of length n minus k, so it can reduce the entropy by at most n minus k. So X still has at least k bits of entropy left. On the other hand, I claim that from A's perspective, at this point, after F and Y, after Y is sent, X has no entropy left. Okay? So, and this follows from the collision resistance of the hash function. So the fact that the hash family is collision resistant means that once A sends Y, right, it can't produce, it's infeasible for A to produce two inputs, X and X prime, that both hash to Y. Otherwise, A would be, if A is a feasible polynomial time algorithm, A would be finding a collision in the hash function F. Okay? So we think of this at an intuitive level of saying that X has entropy, has real entropy given Y and F, but it's inaccessible to A. Okay? And so to make this more precise, we have to think not just of this A that I've described here, this honest A that follows the protocol, because clearly this A, it will always send the X that it's chosen. If you sort of condition on what A knows at this point, namely this value X, then there's no randomness left in the system. Okay? So here we want to think of an adversarial A that may not follow the game as described here, okay? And may toss some additional coins at this point in trying to generate an X with a lot of entropy. And we want to say that that is infeasible. Okay, so let's consider a cheating A star. All right, so now it receives F from B, tosses some coins, we'll denote by S1, sends some value Y depending on that. It may get it by choosing an input and evaluating, it may do it in some other way. And now tosses some more coins, trying to get entropy in X. And the claim is that the collision resistance of the hash function means that X is essentially determined by A's state after sending Y, namely by F and S1. Okay? And you include Y, but Y is a function of F and S1. So that is, there's a function, for every A star, there's a function mapping F, Y, and S1, that's A's state after sending Y, to a unique value X, such that this is the value that A star will send, except with negligible probability. Okay? Even though A is tossing fresh random coins, is trying to generate X with a lot of entropy, it can't. Given these things, X is almost uniquely determined. All right, so one small modification, we have to allow the possibility that A sends something invalid that's not a pre-image of Y under the hash function F. So what it really does, either sends this unique value that's pi of F, Y, and S1, or something that's not a pre-image, an invalid message. Okay, so here, in contrast to the pseudo-entropy that we talked about before, we have a situation where the real entropy of X, say from B's perspective, is high given the past, but from A's perspective, computationally, it looks like it has low entropy. So a difference between what we're trying to capture here and what was before is here the computational form of entropy is smaller than the real entropy. Okay, so now let's forget this example of collision-resistant hash function. Just consider this question. We want to come up with some computational analog of entropy that captures the possibility that a random variable, in a useful and interesting way, that the computational entropy in a random variable can be much smaller than its real entropy. All right, so a first attempt would be to try and use something just like the definition of Husted et al. From earlier. We say a random variable X has accessible entropy, or you can even call it pseudo-entropy if you like, at most K, if there is a random variable, if it is indistinguishable from some random variable of low entropy, whose actual entropy is low. Computationally indistinguishable from something of actually low entropy. And the claim is that this definition is not a useful one. Okay, it's not really an interesting one. It turns out that every random variable X is computationally indistinguishable from a random variable of very low entropy. Okay, this can be proved just by a probabilistic method, if you take slightly super polynomial number of random samples from X and let Y just be the uniform distribution on those, or on that multi-set of samples, then with very high probability, Y will be computationally indistinguishable from X by, say, circuits of polynomial size, and yet the entropy of Y will be just slightly super logarithmic, because its support size is just slightly super polynomial. Okay? And if you want to preserve efficient sampleability, instead you could just compose X with the sampling algorithm for X with a pseudorandom generator and get the same kind of conclusion. Okay, so this definition is not, this Hill notion is not useful for capturing the idea that a computational entropy can be smaller than the real entropy. All right, so instead, let's try and have a definition that really comes from thinking about this example we have. All right, so again, we'll think of, in the applications we're interested in are of this type, we'll think of an interactive protocol between two parties, A and B, and we want to think of it as having what we call inaccessible entropy if the actual entropy of A's messages, okay, from B's point of view, is larger, noticeably larger, than the entropy that A, or a cheating strategy for A star, can generate from its own point of view. Meaning, so given the transcript so far, the messages have a lot of entropy, but given the state of A, or the adversary, A star, they don't have much entropy. All right, and so we refer to this first quantity, again, we'll refer to it as real entropy. Well, I'll be more precise, but we'll refer to this as real entropy, and then this latter quantity, or upper bound, we'll refer to as the accessible entropy, or what is accessible by a feasible adversary. All right, so let's now make these more precise. So we have this protocol between A and B. B sends a message B1 to A, then A sends a response A1, B2. We denote that random variables for when they play honestly with each other like this. And we say that the real entropy of A's messages in this protocol is just the sum of their conditional probabilities, the entropy, conditional entropy. So the conditional entropy of A1 given the past, B1, conditional entropy of A2 given the past up to there, B1, A1, B2, and so on. And we sum this over all the realms. Okay? One remark is, for simplicity, we are only considering the case that B actually follows the protocol. In general, and in applications, it can be useful, and the definitions generalize naturally, and our constructions do as well, to the case where you will actually talk about the entropy even when B deviates from the protocol. Well, that's just a side remark for experts. Okay, so accessible entropy. Now, we consider a possibly cheating strategy A star, okay, playing against B. So B sends its first message B1. Now A star, at every round, will toss some coins. We'll denote the first set of coins that A star tosses S1. It sends a message A1 to B based on that. All right. But now, in addition, we need to capture, if you think back to the collision resistance example, the constraint that A star should send only valid messages, right? And how that's captured is that at this time, A star should also output a witness, W, which we'll denote by W1, that justifies this message as being a valid one that an honest A would have sent. Okay, so I'll elaborate on that. So at each round, A tosses some coins, like S1 here, sends a message, A1, and then privately, this is not something it sends to B, privately outputs this witness, WI, in the ith round, that justifies the message. And in our applications, you can think of this as coin tosses for the honest A that are consistent with the messages that have been sent so far. That if the honest A had these coin tosses, it would have sent exactly the messages that I've sent. Okay? And so if someone stops A star and says, I think you've been cheating, show me that you've been behaving like the honest A, that you're behaving honestly. It says, well, here, my coin tosses, the honest A would have sent exactly the messages I've sent if it had these coin tosses. Okay? And it does this at each round. Okay? And it may change its mind about what coin tosses for the honest A it would declare if you stopped it at any point in time. All right? And in an application, that's exactly what we would do ultimately is stop A star at some point and say, show me your coin tosses. Okay, so now we say the protocol has accessible entropy at most k if for every feasible strategy A star, the sum of conditional entropes it can achieve is at most k, but here we condition not just on the transcript so far, but we condition also on all the coins that A star has tossed in prior rounds. So when we talk about the entropy of A2, we also condition on the coins S1 and so on. Okay? And this is similar to what we talked about in encryption, that the two measures of entropy are really talking about from two parties, sort of different perspectives, the honest perspective and the adversary's perspective. Here it's B's perspective versus the real entropy is from sort of B's perspective, and accessible entropy is from A, or cheating A's perspective. All right, so a couple of remarks on this definition. So again, we need to handle the possibility that A star may output invalid justifications. Okay? And in some sense, what you want to do is count zero entropy in those cases when an invalid justification is provided. So we have a way of sort of taking that into account in our measure of entropy that I don't want to get into in the talk. So you want to sort of quantify it in the right way. But for the purpose of the talk, we'll just assume that A star always produces a valid justification. Right. A second remark to show that this is really a computational notion of entropy is that if we remove the computational constraints on A star, then I claim that there's a strategy for it that achieves really that achieves entropy equal to the real entropy. And what is this A star strategy? At each round, what A star will do is it looks at the history so far. It will sample uniformly random coin tosses for A that are consistent with the history so far, and then send a message based on that. Okay? And it turns out that then the distribution on the transcript, then this achieves exactly a distribution of next message conditioned on A star state so far that's the same as the distribution of the honest A's message conditioned on the history so far.
So this means that this cannot exist also without one-way functions.
That's right. And our main, the main step in our application of this notion is going the other direction, saying that from a one-way function we can build a protocol with a gap between accessible and real entropy.
Like in Halias 11.
I'm not sure maybe we haven't looked into connection with Halias 11.
Well, you talked about something, A's behavior. If there were no one-way functions, you could sample the behavior of any efficient algorithm using it.
You're saying, okay, good. All right, so you're saying, all right, so this is the proof that a gap between real entropy and accessible entropy implies the existence of one-way functions. The one-way functions are necessary. What we've seen so far with collision-resistant hashing, and I'll go back to that example, that collision-resistant hash functions imply protocols where there's a gap. So, and what we will show is from sort of a converse to what you get from Halias 11, that from a one-way function you can build something with a gap. Okay, so let's go back to this collision-resistant function example. So again, we have random function sent by B, and then A sends an point in the range. Honestly, would be by evaluating F on a random point, and then a pre-image. So the real entropy here. So now, okay, in our definition, notice we're counting the entropy summing over all messages of A. The definition, and in our applications also, it sometimes is useful to look at summing over a subset of the rounds, not all the messages of A. But here, let's work with the definition where we do sum over all the rounds. So the entropy of y given f plus the entropy of x given y and f for the real entropy. So the entropy of y given, if you look at the sum of these two things, then by the chain rule, this is just the entropy of x given f. And the intuition for that is that all the entropy of A's messages are contained in x, because y is a function of x. And what is the entropy of x given f? Well, x is taken independently and randomly from f, so it's just n. It's a real entropy. On the other hand, the accessible entropy we claim is basically n minus k. All right, so the entropy of y given f is at most n minus k, because y is of length at most n minus k. And now from what we said before, the entropy of x, given the state of A so far, that's f, s1, and y, is negligible because, as we said before, the collision resistance of the hash function implies that x is a function of these things, except with negligible probability. Okay, but we're interested, so sort of this example of collision-resistant hashing is really using this accessible entropy only in this sort of qualitative extreme where something is entirely determined, so the value, accessible entropy 0, or negligible. So in our applications, we'll be interested in this more quantitative measure, and we'll see how it comes up. Okay, our main applications are to constructions of commitment schemes, so let me review what a commitment scheme is. So commitment scheme is a cryptographic analog of a safe. All right, there are two stages to a commitment scheme. In the first stage, so we have a sender S and a receiver R. Sender has some secret or private message M it wants to commit to. And the commit stage corresponds to putting the message in the safe, locking it, sending the safe to the receiver. And then later, if the parties so choose, they can go through the reveal stage of the commitment scheme where the sender basically allows the receiver to open the safe and see the contents. Okay? So mathematically, what you have is a sort of two-stage protocol. So in the first stage of the protocol, so the sender has this n-bit message M. They undergo a possibly interactive protocol here where S is committing to M. That corresponds to putting the message in the safe and sending it to the receiver. And then later, the sender can reveal the message together with a key. And this sort of corresponds to the receiver checking that M is the message that was committed to in the first stage, and will accept or reject accordingly, whether the things are consistent. Without loss of generality, this reveal stage is non-interactive, and actually can just consist of the coin tosses that the sender used in the commit stage. All right, so what are the security properties of a commitment scheme? There are two. One that protects the sender is called a hiding property. This is a secrecy condition. It says that after the commit stage, the receiver should have no idea what the sender committed to. So that a commitment of one message should be indistinguishable from a commitment to another message. And this comes in two flavors. It can be statistically indistinguishable, sort of analogous to Shannon's perfect secrecy or statistical generalization of it, or computational hiding, where they're only computationally indistinguishable. And the binding property says a cheating sender is bound to, it can't change the value in the safe after the commit stage. So it is, the cheating sender can't produce accepting valid decommitments in the reveal stage to two distinct messages, except with negligible probability. And this also comes both in a statistical flavor, where we require security against computationally unbounded cheating senders, S star, and a computational version, where you only require this for feasible polynomial time strategies. All right, so statistical security in both cases is clearly stronger than computational. You have security against even a computationally unbounded adversary. But unfortunately, it's not hard to show that you can't have commitment schemes that are simultaneously statistically hiding and statistically binding. Okay, if the message is information theoretically determined at the end of the commit stage, then it can't be information theoretically hidden if you have unbounded resources. So the best you can hope for is to have one condition or the other be statistical. In the case of statistical binding, we've had a very good understanding of for a long time. And specifically the works of Hastad et al. That I mentioned earlier, constructing pseudorandom generators from one-way functions, and work of Naor, constructing statistically binding commitments from pseudorandom generators, showed that you can build statistically binding commitments from the minimal complexity assumption for complexity-based cryptography, namely the existence of one-way functions. The other case, where you want the hiding to be statistical, but are happy with the binding being computational, It's only a couple of years ago, in joint work with Iftach Heitner, Min Nguyen, Shenjin Ong, and Omer Reingold, that we were able to show that you can build statistically hiding commitments from any one-way function. There were a series of earlier works showing how to build statistically hiding commitments from progressively weaker and weaker assumptions leading up to this result. Okay, but for the purposes of this talk, so this is a previous work, purpose of this work, a problem with this result is that, at least from our perspective, it was too complicated. Both the construction and its analysis, too complicated, didn't feel like the right proof of this result. So our first application of this notion of accessible or inaccessible entropy is a much simpler proof of this result, that you can build statistically hiding commitments from any one-way function. And the nice thing about it is that the new construction and its analysis really parallels the construction of statistically binding commitments due to Hastad et al. And Naor. So a joke that Omer made is that so traditionally the work of Hastad et al. used to be thought of as a complicated result in cryptography, and our goal in this work was to make statistically hiding commitments as simple as Hill. But really, from today's perspective, I think Hastad et al. Is no longer really such a complicated result. And there have also been some nice works recently simplifying the most complex parts of it. Sort of given what we know today about sort of how commonly we use entropy and randomness extraction and these sorts of things. And so that's more or less what we achieved. And there are some other side benefits. We also can achieve optimal round complexity, namely n over log n if you're starting with a one-way function on n bits, for at least a non-uniform version where the honest parties require some non-uniform advice to run the protocol. And for a uniform version, we just get the square of this. The lower bound that shows that n over log n is optimal is due to Heitner, Hock, Reingold, and Segev. And this compares to the previous construction. There was some large polynomial number of rounds that was not even specified. Okay, so a second result, which I won't talk about in any detail at all, regards the relationship between round-efficient statistically hiding commitments, so constant round ones, which can't be built from one-way functions, at least in a black box manner, by this lower bound that I just mentioned, and round-efficient zero-knowledge proofs. And specifically, it shows that NP has constant round zero-knowledge proofs with black box simulation. Don't worry about what that is if you don't know. That remains zero-knowledge under parallel composition, if you repeat it many times in parallel, if and only if constant round statistically hiding commitments exist. All right, so one direction has been known for a long time, that you can go from constant round statistically hiding commitments to constant round zero knowledge, and our main contribution is an application of accessible entropy is to prove a converse. Okay, so one thing is that we really wanted to show this result without assuming that the zero knowledge is closed under parallel composition, just to assume that it has negligible soundness error, and that's an interesting open problem on the left here. Okay, so I won't get to say much about the details of the first application, but let's at least see what is the connection between statistically hiding commitments and inaccessible entropy. So now again, like we did with encryption, let's think of committing to a uniformly random n-bit message, and we'll let C be a random variable denoting the transcript of the commit stage, and M, the value that's revealed. And then, again, we'll separate this from the key, K, which we think of as a justification for the message M that's revealed. So what is statistical hiding property? It says that the commit stage reveals no information, or statistically no information, about the message M. All right? And that can be translated into saying that the real entropy of M, given the transcript so far, given C, so from the receiver, this is capturing what the receiver sees, is nearly n minus negligible. On the other hand, the computational binding property says that from the sender's perspective, the message is uniquely determined after the commit stage. So that is, if we consider a cheating sender, we could toss some coins in the commit stage, and then allow it to toss possibly additional coins in the reveal stage. It can't generate, it's stuck to basically 0 or negligible entropy in M if we condition on C, on its state after the commit stage, namely C and its coins S1. Okay? So this looks, really, this is just like what we were capturing with inaccessible entropy. Real entropy, very high, same as the uniform distribution, up to a negligible amount, and accessible entropy, negligibly close to 0. Okay, so there is really a very close connection, and our goal is to construct that from any one-way function. And our proof really goes along very similar lines to what I mentioned about the work of Hastad et al. Earlier. So our first step, starting from a one-way function, we build a protocol where there's a slight gap between its real entropy and its computationally accessible entropy. Okay? Not a very big gap. It turns out it's log n bits, but the total amount of entropy we're talking about is polynomial, so it's not huge. And this is using a beautiful protocol of Naor, Ostrovsky, Venkatesan, and Young called interactive hashing, and a kind of generalization of Heitner and Reingold. It was used by Naor et al. To build statistically hiding commitments from one-way permutations, one-way functions that are permutations, say, on n-bit strings. They showed that this construction gives a statistically hiding commitment in one shot. And our observation here is that if you apply it to an arbitrary one-way function, so you may not get a statistically hiding commitment out right away, but what you get is a slight gap between real entropy and accessible entropy. And then things really parallel Hastad et al. Construction. You take repetitions. This makes the entropy gap larger. It also converts the real Shannon entropy into min entropy. Unfortunately, it doesn't convert the accessible entropy into accessible max entropy, but I don't want to get too much into that issue right now. And then we do some hashing to convert the high min entropy into almost uniform distribution, like we want for statistically hiding commitment, and to convert the low accessible entropy into kind of negligible, almost 0 entropy, which corresponds to binding. And this turns out you can't just use universal hashing like in Hill et al., but we can use a slightly interactive form of hashing, constant round protocol due to Ding, Harnick, Rosen, and Chaltiel. And it's kind of two rounds of hashing, plus something called universal one-way hash functions, which are kind of a weaker analog of collision-resistant hash functions, which can be built from any one-way function by work with Rompel. Now, you'd think that we're done, except the problem here is that accessible entropy talks about protocols with many rounds, and so you get really sort of many rounds where in every round you have hiding in all the rounds, and you must be binding at least once. All right. So anyway, the catch here is you get something of kind of that looks like many commitments executed sequentially with some relationship between their security properties. And then we do some sort of simple cut-and-choose protocol, deciding the receiver randomly decides which one will be the actual commitment to get a standard statistically hiding commitment. Okay, so that's about all I'll be able to say about the proof. Just want to show how this really, especially the first 3 steps, really parallel what happens in the construction of pseudo-random generators and hence statistically binding commitments from one-way functions. It differs a bit in the final step in the 2 cases. Okay, I won't have time to talk about this first step. Just the protocol is actually very simple. The analysis takes a little bit more time. Basically, A evaluates the one-way function on the random input, and then sends random 1-bit hashes of the output Y to B in each round, according to hash functions chosen by B, and then reveals X. And so the protocol is simple. The analysis takes a little more time. I didn't really expect to get through this, but it was fun to make these animations anyhow. Okay, so to conclude, I just want to conclude with the thesis that complexity-based cryptography is possible because of gaps between real entropy and computational forms of entropy. And we're very familiar with this for secrecy in cryptography, that secrecy corresponds to having computational entropy, namely pseudo-entropy, larger than real entropy. And what we show in this work is that there's an analogous phenomenon for unforgeability conditions, which correspond to having a computational form of entropy, namely accessible entropy, be noticeably smaller than the real entropy. And there are a lot of concrete open questions, but I just want to end with a sort of more general question of what else is this. We gave a couple of applications here. What else is this notion of inaccessible entropy good for? Oh, great. So Avi asked, is there a definition of inaccessible entropy that can make sense not in interactive protocol settings? And we were really led to this interactive protocol setting because that's the sort of applications also we were looking at were naturally interactive. So we've only recently sort of started thinking about what other ways in which you could have it. So you do need there to be some asymmetry between, when you want to have a gap between real entropy and computational entropy, and if your real entropy is achieved by an efficient, honest party, which is what you really want, you need there to be some asymmetry in order to have this gap, because otherwise the adversary could just be the honest party. So you can't just say, I have a distribution that, can be sampled of high entropy by an efficient algorithm, but can't be sampled by high entropy by an efficient algorithm, because those two, right? But you could get this non-interactive asymmetry by some sort of secret key. And I think this is what corresponds if you start trying to model message authentication codes and digital signatures. So then it becomes non-interactive. So with a secret key, you have a distribution that you can sample of high entropy. So for example, I can generate a uniformly random message together with a justification, a digital signature or a MAC of it. But an efficient algorithm without the key can't generate a high entropy distribution. So that seems to be the way to get a non-interactive definition, is the asymmetry, instead of coming from interaction and conditioning, whether we condition on the state or the history, we get the asymmetry by possession of a secret key. And then you may have an... so we do know how to simplify, or at least cast Rumpel's, the construction of universal one-way hash functions from one-way functions in the language of inaccessible entropy. I never actually have understood Rumpel's construction myself, so I can't tell you whether it's simpler or not. You'd have to ask Yiftach.
Thanks for coming. I'm not supposed to have these microphones that made the previous speakers so impressive. Underneath? Okay. That's how it works. So the title is Color Coding, Bayes Hashing, and Proximate Counting. And most of this is joint work with Shai Butner, but I thought that you deserve more, so I added to the title and more, and the more part, this will be just at the very end. This will be a part from a recent joint work with Daniel Lokshtanov and Saket Sauran. So let me start with color coding, and here is a question. So this question was raised some time ago by Christos Papadimitriou and Mihalis Yanakakis, and they asked the following: is it possible to decide in polynomial time if a given graph with n vertices, let's say undirected, contains a path of length exactly log base 2 of n, let's say integer part? Now this looks somewhat specific, but you know that the old Greeks always know to ask the right questions. They were actually not so old at that time, and they are also not so Greeks now. But still, it turns out that this was indeed somehow a good question because indeed it leads to many related things. And I'll try to tell you about this. Of course, this is all old, so maybe many of you have seen it. So we noticed with Rafi Uster and Uri Zwick that this answer is yes, that indeed this can be done. And in fact, it's very simple, so I can really describe it in a few lines, and this is what I try to do here. So we'll first describe a randomized algorithm, and afterwards we will de-randomize it, convert it into a deterministic algorithm. And indeed, I think about this as a good example that illustrates the fact that often probabilistic reasoning is helpful. So it's even if you care only about deterministic algorithms, sometimes it's better to first think of a randomized algorithm and then to convert it into a deterministic one. So let's describe a simple randomized algorithm. What we do is that we color the vertices randomly by k colors. And after they are colored by k colors, so k is the number of vertices in the path I'm looking for. Let's call a path multicolored. Let's see if this... right, so a path is multicolored if all its vertices get distinct colors. Now we want to find efficiently if there is a multicolored k-path for this given coloring using dynamic programming. And that's simple. I say a few words about this, but it's simple to see that indeed this can be done quickly. And basically that's it, right? So that will be the algorithm. If we, maybe we'll repeat it several times, if we find a multicolored k-path, then definitely there is a k-path. If we did it several times, we'll soon see how many times, and we didn't find a k-path, then we'll say that probably there isn't a k-path, and with high probability it will be correct. So here is the relevant computation. The probability that the path of k vertices will become multicolored is exactly k factorial over k to the k, which is roughly e to the minus k, so it's exponentially small in k. And therefore, if we do it about e to the k times, we will expect that if there is a path there, then it will become multicolored. Now, a few words about the dynamic programming. So I just wrote here what we have to do it. Basically, it's a simple exercise. So for every vertex v and every subset t of the set of the colors, we just check if there is a multicolored path of size t, the cardinality of t, many vertices, ending at the vertex v, using exactly the colors in t. Okay? And so this is easy to start, and it's easy to update it. Because if we have things for sets of size I minus 1, then we can easily generate the required things for sets of size I. So maybe you see it immediately. If not, you have to think 2 minutes, but this is really simple. So that's the whole randomized algorithm. Let me mention that, so this basically gives the expected running time 2e to the k roughly, because we have to repeat it e to the k times because of the probability, and the running time is roughly 2 to the k for each specific, I mean, maybe I have to multiply it here by the size of the graph. Okay, so that's the dependence on k, and there is also a linear dependence on the size of the graph. And actually, there is a recent result by Yannis Koutis and Ryan Williams that shows how to improve this, again, in a randomized algorithm to roughly 2 to the k. And the trick is that we color, instead of coloring by usual colors, we color by elements of the right group algebra. So we take the group z2 to the k with the coefficients in a field of characteristic 2, large field of characteristic 2, and somehow if we color by elements of this field, we have to say something, but then this will give us an improved expected running time. But as I said, we want really a deterministic algorithm. That was also this question of Papadimitriou and Yannakakis, and indeed this can be de-randomized easily, in fact, because you just have to kind of use what's known about perfect hashing. So the idea is to use or to observe that explicit schemes of perfect hashings give us explicit families of size 2 to the OK, let's say, times log n. I mean, the base construction roughly e to the k times log n. Colorings of a set of size n, this will be v, by k colors, so that every set of size k will be multicolored, namely will get distinct colors in at least one of the colorings. Okay, and the specific references start with this hashing scheme by Mike Friedman, Janusz Komlosh, and Andres Emeredy, and then there is a somewhat more explicit way by Jeanette Schmidt and Ellen Siegel, and a better dependence on the parameters by Moni Noor, Leonard Schulman, and Darwin Srinivasan. And basically the last word is that the size or the number of colorings in the family is roughly e to the k times log n. Okay, so it's written here that this stands for finding copies of any graph with bounded tree width. So instead of path, we can try to find cycles or some specific trees or some serious parallel graphs, so some other things as well. It's basically the same thing. And as I said at the beginning, I think this is a nice example where indeed you see that even if you care about a deterministic algorithm, it helps to think randomly, because if you look at the code when this is implemented, then most of the code will just do all kinds of operations in finite fields, maybe, that have to do with generating these explicit families of hash functions. And only at the very end, the algorithm will actually start looking at the graph, will do very simple things about the graph, just the dynamic programming that I described, and then we'll answer if there is a path or there is no path. And somehow probably we would not think about an algorithm like that if we don't start by thinking randomly. Okay, so this is about deciding if there is a path of length k or not. Now it turns out that this is useful in at least in the literature about computational biology, and in fact this increased the number of spam I get quite significantly, because I get all the announcements on the conferences and publications about C. elegans. So C. elegans is what you see here. That's a worm, which is the first multicellular organism whose genome has been completely sequenced, and it is smaller than what you see here. It is 1 millimeter long, and apparently when looking at protein interaction networks of this thing and some other organisms, then it's common to look for appearances of what is called motifs, which are basically appearances of some specific subgraphs of some relatively small size in a given graph, which represents some network of this kind, and maybe we want to know if some such network contains a path or a cycle of a given length, or some trees, for example, because we want to know how similar two such networks are to each other. Okay, now this application actually suggests that maybe more than deciding if these subgraphs exist there or not, we would actually want to count them also. And I prefer to speak about path. Everything that I say here indeed extends to other graphs of bounded tree width, but it's good enough to think about path only. So suppose that now I have a graph, again, on n vertices, and I want to count, and let's say that now I want to count precisely how many paths it has on k vertices. Okay? This would also be useful. And you see the dynamic programming, because it's so simple and so general, it can easily be used also to count multicolored paths. If we really color vertices randomly or not randomly by some k colors, then we can decide quickly in essentially linear time. Not only can we decide if there is one path of length k, but we can actually count the number of paths of length k, because instead of what I said before is that we maintain for each vertex and for each set of vertices, if there is a path using the colors in this set of colors, a path of the corresponding length that ends in that vertex, we just maintain the number of such paths that end at that vertex, and again, it's easy to update it. But then, of course, if we know to do it for one coloring, and if we want to count precisely how many paths of length k we have, then what we have to do is to find a family of colorings that will be completely balanced, in the sense that every set of size k, which is a potential path, will be multicolored exactly the same number of times. And this number of times has to be positive. And if this will be the case, then if we will do the double counting, it will give us the exact number of paths that exist in our graph. Okay, so this suggests to define what's called balanced families of hash functions, and here is the definition. So we call a family of functions from n to k, and we think about it just as colorings of the set of n vertices of a graph by k colors. We'll call it a perfectly balanced family of hash functions if there is some positive number, t, so that every subset k of this set of vertices, which is of size little k, the number of functions f that map k in a one-to-one fashion is exactly t. Namely, every set of k vertices will be colored in a one-to-one fashion. We'll use all the colors in exactly the same number of times. Right? And again, as I said, this is exactly what, so this is this balanced family of hash functions, and this is exactly what we need in order to count paths precisely, because then if I'll have such a family, and for each such coloring, I'll count how many multicolored paths I have with respect to this coloring, then I'll count every path exactly t times. So I'll sum it all, and I'll divide by t, and this will give me the number of paths. Okay, so the hope is that there are such families, and hopefully also explicit, and maybe they don't contain too many functions, but this is not the case, because in fact such families must be large. Well, how large, we don't know precisely, but at least we can show that they have to be of size at least n to the k over 2, or the integer part of k over 2, and there are some simple constructions where they are of size n to the k minus 1, maybe. And I want to show a proof of this, trying to challenge the fact that we cannot show any proof that takes more than 2 lines in a PowerPoint presentation. So maybe this will be 10 lines or so, but it's a simple proof, and it's somehow a nice linear algebra proof. So let me try to describe it. So suppose we have such a family. Every set of size k is colored, or the image of it is of size k also in exactly t times, and we want to show that the family is big. So what is usually done when we try to use this linear algebra approach is that we define some vectors, and we show that they are linearly independent, and this will give us some bound, because the dimension of the space generated by these vectors cannot be more than their length. So here is how we do it here. So we define for each set of size k over 2, each k over 2 vertices, or things that get a color, we define 2 vectors that are denoted here by this u sub r and wr. So these are the 2 vectors. And they will be of length, some constant depending on k, which here will be k choose k over 2, so about 2 to the k, times the cardinality of A. So the length is up to a constant depending on k, the cardinality of F. and the coordinates of each such vector are indexed by the ordered pairs f and s, where f is a function in our family, and s is a subset of the set of colors of size k over 2. Okay? And here is the definition. So for the first vector, ur in coordinate fs will be 1 if and only if the function f maps r into s. Okay, so necessarily it is in a one-to-one manner because they are both of the same size, k over 2, so let's assume for now that k is even. Now for w we do something similar. The vector wr maps in coordinate fs is 1 if and only if f maps r to the complement of s, to k minus s. Okay? And here comes the problem because we have to move to another page, but okay. And then the thing to observe is that the inner product of two such vectors, ur and wq, will be 0 if the two sets R and Q intersect, and will be exactly T if they are disjoint. So let's go back here, not so much. Let's go back here and look again at the vectors. So what is the inner product between two such vectors? Well, it counts the number of pairs Fs in which we see 1 in both vectors, because this is what will contribute to the inner product. Now, if so if we have here the U corresponding to R and the W corresponding to Q, and R and Q are not disjoint, then certainly they cannot map R to two disjoint things. And therefore this will never happen if they are not disjoint. But if they are disjoint and F maps their union in a one-to-one way, then exactly there will be one place in which we'll see 1 in both places. Okay, so I see. So this is simple. And because of this, it means that the product of the matrix whose rows are the vectors UR with the matrix whose columns are the vectors WQ is exactly what's called the disjointness matrix. Namely, it will be a matrix whose rows and columns are indexed by sets of size k over 2 in n, and it will be 0 if the sets are not disjoint. If they are disjoint, it will give us exactly T. So it is a disjointness matrix times T. It is known and simple that this matrix has full rank over the reals, and because of this also both matrices in the product have at least the same rank, and because of this the number of columns, let's say in the first matrix, is at least the rank of this product, and this is what's written here, which gives us the lower bound for f. So f is at least n to the k over 2. As I said, you can show that n to the k minus 1 times some constant is an upper bound. In fact, if we really care, we can show that for k equals 2, the precise minimum is n if and only if there is no Hadamard matrix of size n by n, and if there is such a matrix, then the precise minimum is n minus 1. Of course, this does not really matter for the asymptotic result, but what this means is that we will not be able to use this thing in order to count path in a given input graph quickly. So we will need at least time n to the k over 2. Actually, it is known that one can count precisely the number of paths in a graph of size n in time about n to the k over 2. That's a recent paper by Williams and Vasilevska. But the fact that we cannot count precisely path more efficiently is actually not surprising, and this leads us to what's known about what's called parameterized complexity. So let me tell you a little bit about this. So this was introduced in the 90s by Downey and Fellows, and there are at least 2 books about it and many papers. And this came from the observation that for many NP-hard problems, they come with a natural parameter. And often it is the case that if this parameter is small, then the algorithmic problem can be actually solved quickly. So maybe the problem is NP hard, so if the parameter is big, then we don't know, and probably there is no polynomial time algorithm. But if the parameter is small, then there is an efficient algorithm. And specifically, the definition is that if we have, so a problem will be called fixed parameter tractable if on input of size n and parameter k, there is an algorithm that runs in time some function of k times fixed polynomial in a. Okay? So for example, what we saw in the beginning is that deciding if a graph of size n contains a path of length k is fixed parameter tractable when the parameter is k. Okay? But on the other hand, at least according to what we know so far, deciding if a graph contains a clique of size k is fixed parameter intractable in the sense that it is complete for one of these corresponding complexity classes. Namely, if we can do this in time that is some function of the parameter times some fixed polynomial, then we can do many other things in a similar way, including many things that we don't know to do. Now it turns out, and this is somewhat surprising, so that's a result by Flum and Grohe, that the problem of counting the number of paths of length k in a graph of size n is complete for one of these, is what's called sharp W1 complete. Namely, if there is an algorithm that will count precisely the number of paths of size k in an input graph of size n in time f of k times n to a fixed power, then there will also be an algorithm that counts the number of cliques of size k in such a graph in a similar running time. And there will be similar algorithms for several other problems. So therefore, it is not surprising that there are no small families of perfectly balanced hash functions, because this would give some collapse for these complexity classes. Okay, but we still have this, that's another picture of this C. elegans. So we still have to know something about these protein interaction networks. And obviously, if we want to know if they are similar, there is no real reason to count precisely the number of subgraphs of a certain type in them. It will be enough to count it approximately, so to know it. And this is what we want to consider next. So suppose that I only want to approximate, and again, let's talk about path. I want to approximate the number of paths of length k up to a relative error of 1%, let's say. And I want to do it randomly, maybe better deterministically. Can I do that? So we already saw that probably we cannot count precisely, but maybe we can count approximately. And for that, again, if we want to still use the same approach of this color coding and using dynamic programming to count multicolored paths, then maybe I first wrote here that to do it randomly is kind of very simple. So in particular, we do it in this paper with Dow, Liha, Homozigiari, and Sainal. I was thinking to say that the algorithm is much, much simpler than the problem of pronouncing the actual names of the co-authors. But so really the paper is more on the applications to these questions in computational biology. But basically, if we just color randomly and count, then using any standard large deviation inequality, it will follow that every set of size k will be colored with distinct colors in about the correct number of times, and therefore we will get, by the double counting, the approximate number of paths or subgraphs of bounded tree width, whatever we are trying to count. So the interesting thing here will be to do it deterministically. And in order to do it deterministically, it's also obvious, again, from the general approach, that what you need is what we call here an epsilon balanced family of hash functions, which is defined in this paper with Shai. And I think we think it can be useful for several other applications as well, because hash functions are so useful, and that's kind of a natural extension. So when is a family of functions, or think about it about colorings of n vertices by k colors, when is it called an epsilon balanced family of hash functions? So here is the definition. We want that there will be some number t, which has to be positive, so that for every subset k of this set of vertices, which is of size k, the number of functions f in the family that map k to distinct colors, so in a one-to-one manner, just gives them all the different k colors, is roughly t. So before we wanted them to be exactly t, now we want it to be at least 1 minus epsilon t, and at most 1 plus epsilon t. And we just think about epsilon as some small fixed positive real. So this is a definition. Now the fact that follows easily from the probabilistic method is that there are such families which are small. Namely, if we just take a size of families that is slightly more than the minimum size of families that is needed for just getting a family of perfect hash functions, namely a family in which every set of size k is mapped by at least one coloring to different colors. So it is known that for these tight lower and upper bounds are these roughly e to the k times log n. Then if we add this little o1 here, then, well, it's in the exponent, so we multiply it by quite a lot, but then a random family of functions will be good with high probability. Every set will be mapped in a one-to-one manner in roughly the same number of times, and that's basically this simple computation that I told you before that exists using Hofding or something. Okay? But of course, we want it in order to de-randomize this randomized algorithm. So the only point is to construct such a family explicitly. And this is what we want to do. And it turns out this can be done. And so here is a statement. The statement is that there exists an explicit construction of an epsilon balanced family of functions. And what is written here is for every epsilon that is let's say 1 over polynomial in k. Okay? So this will be functions from n to k. K is the number of colors. The number of functions will be as small as it can be, again, up to this little o1k. So of course, little o1k is bigger than what it should be in the minimum, but it's essentially e to the k times log n. And it can be constructed in time which is essentially linear, so almost linear up to well, I guess up to all these little o1 factors. So essentially linear in the number of in the time it takes to write down the functions. So I should say that it's not as explicit as some explicit constructions are. Sometimes we want that explicit constructions will be in log space or in a, but here for the application, we don't really care, right? We anyway have to use these colorings afterwards, and for each coloring, we are going to do something about the graph and to count paths. So it's enough that we can really construct this in times that it takes to write them down. And that's essentially what is known for usual constructions of families of hash functions if we insist on the best dependence of the parameters. Now, the construction is a bit technical, so it uses two relatively standard steps, and these are the first and the last. So I wrote here small sample spaces supporting nearly pairwise independent random variables. This is basically to start with some version of hashing, and the last step is a method of conditional expectations, which is also quite standard. The middle step is technically quite involved, and that's some recursive construction based on some properties of expanders. And so I could try, but I decided that I don't want to describe the details here. But this takes some efforts. Let me also mention that so this will be this family of functions, and every set of size k let's say, k vertices, if you think about these functions as coloring of the vertices, every set of size k will be colored by the k distinct colors in about the same number of times, so between 1 minus epsilon t and 1 plus epsilon t. And it's interesting to note that this t will not be the right number of times. So it will not be the same number of times that you will get if you will take really random functions. Maybe it will be actually smaller. So we will not have as many functions that make them, the probabilities that a random function in this family maps this set of size k in a one-to-one fashion will not be k factorial over k to the k, but will be somewhat smaller, and this is somehow something that follows because of the properties of this construction, and which means that it's not exactly a de-randomization of the randomized construction, but you have to work. Okay, so I said that I don't want to talk about the technical details of this, but let me just mention that what it implies is that that we can approximate the number of k paths or any other given graph of size k and bounded tree width in a given input graph up to a relative error of 1 over polynomial in k, let's say 1% if you want, in time which is exponential in this k and nearly linear in the size of the input graph. Okay. Fine. So I still have almost 15 minutes to the and more. So let me talk about the more. So it's very related, and that's why I thought that it's useful to tell you about it. And it's some other variant of color coding, which seems to be again useful for some of these algorithmic problems. And I'll just tell you what it is, and I'll show only one application. And as I'll mention, there are a few more. So this is in a joint paper with Lokshtanov and Saurabh. And the corresponding definition here, so this is this thing that we want to construct, and I'll only tell you that we can construct, but so it's something that is slightly more complicated than families of perfect hash functions. This will be a family of functions from a set of size m, and again, it's good to think about it as a set of vertices of graph to R. So let's say that now the number of colors is this R. And let's call it a universal MKR coloring family if it has the following property. Whenever we have a graph G on the set of vertices M, and the graph does not have too many edges, so it has at most k edges, then at least one of our colorings colors this graph properly. So it's a proper vertex coloring of the graph. And I wrote it here that in particular such a family has to be a perfect hash family for sets of size square root k, because maybe the graph is a clique of size square root k that has less than k edges. So this clique, the vertices have to be mapped into distinct colors, but it should be good for other graphs as well, right? So even for a matching of size k, whenever you take k pairs of vertices in this graph, then one of your colors would have to, okay, so it will have to take care of all the graphs of size k. So this is a universal MKR coloring family, and the statement, and again, I won't show the construction, but that there is an explicit family of roughly 2 to the square root k, so there is some logarithmic factor in the exponent here, logarithmic in k, times log n functions from n, from a set of size n, let's say the vertex of a graph of size n, to k colors, and this will be universal, so again up to this log, nk square root k, universal coloring family. Namely, this is a family of colorings of the vertices of a graph on n vertices by about square root k colors, and every graph with at most k edges is colored properly by at least one of these coloring. And as we said, this is, so in particular, this has to be a perfect hash family for sets of size square root k, and therefore by the known lower bound for hashing, the number of functions have to be about e to the square root k times log n. So up to this, just a second, up to this log factor, this will be tight. Question? Or?
What if you make them just good, perfect hash function on all the vertices in this graph?
Yeah, but then they will be, you mean for sets of size k? So then we will have here, we will have here 2 to the k, right? The number of vertices is not serious, right? Yeah, it's always, right. So the important thing here is the behavior on the k, that is square root. The number of vertices, we think about it as much, much bigger. And usually in all these questions, you can easily somehow, as a first step, reduce the number of vertices to k square or something. Yeah, so really is yeah. So the main thing is that the dependence on k. And I'll show you one application of this, which is simple to explain. And this is a feedback arc set problem for tournaments. Okay, this is so what is this? So here is a tournament. A tournament is an oriented complete graph. You see here an oriented complete graph, and which here is quite simple. And the feedback arc set is a set of arcs whose reversal makes it acyclic, okay, or whose reversal or whose omission, it's the same. But so here, for example, we can take this and reverse it. We were talking before if using PowerPoint is better than using Beamer, and I mentioned that PowerPoint is much better for animation, but then I said that normally I never have time and I hardly use animation, but you see that here I use this complicated animation, so try to do it in Beamer. Yeah. But it's, okay, but still, it's in principle it is better. Okay, so this is a feedback arc set. So I think that's clear. Tournament is an oriented complete graph, and a feedback arc set. We want a set of arcs whose reversal makes it acyclic. And usually we want to find the minimum feedback arc set, right? Because a tournament, so you have this, I don't know, basketball teams, every pair had a match with each other, and then you're trying to decide an order which will tell you which is best and which is worst. And the reasonable criterion is to decide that we want to order them in such a way that the number of arcs that go backwards will be minimized. Okay, so as is the case, okay, and it's written that the feedback arc set for tournaments is given T and K. Does T have a feedback arc set of size at most K? Because again, maybe I want to look at the case where K is relatively small. But first, so it is known that this problem is NP hard. This was actually open, so it was the conjecture of Jürgen Bang-Jensen and Karsten Thomassen for a while. And then Eilon, Charikar, and Newman found a way to show that it's NP-hard under randomized reductions, and I realized how this can be de-randomized, this proof. So indeed, this problem is NP-hard, even for tournaments. So given a tournament, deciding what is the minimum number of arcs you have to reverse in order to make it acyclic is NP-hard. So we could try to approximate it, and there are some nice papers about that, and we can try to look about the parameterized version, namely to solve it when k is relatively small. And people looked at that as well, and in fact, here is one paper that does it in time which is polynomial. So again, it is fixed parameter tractable. If the parameter is a number of arcs we have to reverse, and it can be solved in time which is a power of n plus exponential in k. When the lectures are not, so I keep computing time all the time, but at least unlike Ronit, I'm not asking after 10 minutes if I'm already have to finish. So it's okay. And here is the new result is that in fact it can be solved in time. So again, n to some fixed power plus 2 to the square root k. So you can still solve it in polynomial time, even if k is log square n, let's say. And it's actually simple to explain. So so it's simple to explain. So let me try to say something about it. So suppose that we have this tournament and we manage to color the vertices so that the graph of all arcs in an optimal feedback arc set is properly t-colored. Well, suppose it is properly 2-colored, because so in this picture, maybe I tried some 2-coloring of the tournament, and maybe I'm lucky, and the graph consisting of all the edges of the optimal feedback arc set is properly 2-colored. Okay? Namely, all these edges are edges that go from here to here. Well, of course, yeah. Here is where I really had to use animation, but I didn't. Anyway, so it's okay. So the thing is that, you see, if this is indeed a good 2-coloring, which, by the way, which is blue in my screen, but anyway, so if this is a good 2-coloring, then in the tournament on each of these pieces here, in the sub-tournament, this has to be acyclic. So I know really the order, in the order I'm looking for. I know the order of the vertices in this part, and I know the order of the vertices in that part. And then it's easy to see that by dynamic programming, I can decide what is now the best order, because if I already put these 2 vertices here and these 3 vertices here in an optimal way, now the next vertex that has to come must be either this next vertex here or that vertex here. And of course, I'm going to use the best order that I had so far on the vertices that are arranged so far. So I can, by dynamic programming, find the best way now to merge like these 2 orders and find the minimum number of arcs that will be oriented backwards. So we can do it in time n to the t, if t is the number of colors. And now it turns out, and that's not difficult to show, although it's kind of a nice exercise, that a random coloring of a graph with k edges by square root k colors is a proper coloring with probability at least 2 to the minus square root k. There are some constants here, but okay. And because of this, if we will use randomization, if we color randomly, we do it 2 to the square root k times. Now there are no logarithmic factors. Then at least once this optimal feedback arc set will be colored properly, and then we'll find it by doing this dynamic programming. And there is some other trick which changes it from 2 to the square root k times some power of n to 2 to the square root k plus some power of n, but let's ignore this and just mention that that de-randomizing it is exactly this universal coloring families, because exactly what we want is a set of colorings so that every set of at most k edges, this is optimal feedback arc set, in at least one of the colorings, the graph that they define will be properly square root k colors, and this will give in the dynamic programming another maybe k to the square root k or something like this. Okay, and just to finish, so there are several specific problems, but I'll not mention them. It just let me just say that these universal coloring families, they can be defined for hypergraphs as well in the obvious way, and the constructions can be extended as well, and this is useful for some problems like betweenness or whatever. So there are some problems that you can define, and it will be interesting to understand better what can be done by this, and also maybe to further explore what can be done by these balanced families of hash functions. And with this, I'll finish, and thank you for your attention.
Okay, so perhaps the first problem in the whole field of, if you wish, in economics, if you look at it in one way, is basically how do we allocate things? And the same thing is probably true of the first problem in computer science, how do we allocate things? From the economic point of view, or at least some economic point of view, an auction is the first way you can do it. You have one object, there are 2 people, let's say, who want this object, and you have to decide which one of them gets the object. And one natural way to solve it is you have some kind of auction between these two people to decide which one of them would get it. It becomes really an auction once you have, rather than let's say a computer science allocation problem, once you take into consideration the distributed nature of the problem. It's the two different people not only have different information, but they only have different wants. Each one of them wants something else. I want me to get the object, you want you to get the object, and that's not the same, not for me at least. So an auction is really the first kind of problem you ask. What kind of allocation do we do of a single unit item? And then, of course, once we look into more complex scenarios, we have a bunch of items that we need to allocate. We start having to have auctions of multiple items. It can be the same, not the same constraints. Then you can start with lots of different questions. And all of auction theory, the starting point of this auction theory is a question, okay, how do we, what are our criteria according to which we want to allocate the items? How do we model the input, if you wish, what the different people want? And the starting point of most of auction theory is what is called the valuation. So what is a valuation? We assume this is like the simplest scenario and the starting point really. You have some kind of value. You like this item at 7. This other guy likes the item at 8. And the question is now, if we want to know which one should get it, 8 seems better than 7. Okay? So the starting point is a valuation. How much does each participant value each possible outcome? If we have lots of units to allocate, for each possible allocation, say, or for each possible joint decision that we need to come to, how much do they value it expressed in some number, some common currency? And the idea of this common currency is that this is something that we can basically add or subtract money from. So when I try to say, what do I want? My utility, what I want, what I aim to optimize, being a rational participant here, is basically the value that I get from the common decision, from the output, minus whatever payments that I have. And this is the normal way that you start modeling in auction theory. Now, as opposed to what at least I thought as a computer scientist starting to look at economics at the beginning, economists do not like the idea of money, at least not in their models. They're perfectly happy with it other places. So the problem with money is that it's not really well defined. I mean, it's not clear that there is some kind of common currency that you can compare my utility with your utility. It's completely reasonable to say, what do I prefer, option A or option B? It's also reasonable to say, ask you the same question, do you prefer option A or option B? But it's very difficult to quantify these two things and say, oh, I prefer option A to B more than you prefer option A to B. Okay, that's problematic, and economists really do not like it, and it's not the choice usually used in most of the rest of economics. Usually, in most of economic theory, they actually prefer working abstractly in terms of my preference relation and your preference relation, and this is considered an assumption, what's called sometimes a quasi-linear assumption. And the quasi-linear is because the money is linear with the rest of the utility, with the rest of the valuation. And now, in this situation, the reason that we're limiting ourselves basically to working in this quasi-linear model, assuming that there is money, is really because of a very strong impossibility result, the Gibber-Satterthwaite result, which basically says that if you want to work in a general model, where we can't move money from one person to another or to the auctioneer, then basically you can't do almost anything that you want in the proper way, taking irrationality into account. And this is a very strong impossibility result. Basically, it's equivalent, it's very similar, not equivalent, very similar to Arrow's theorem, showing that you cannot do any kind of proper social choice under certain assumptions. But here, it really shows that you cannot do anything once you're outside of this quasi-linear model. And that's why auction theorists are happy working with money. Now, I have to admit that from my point of view, at the beginning, I thought that this was I didn't understand the obsession of economists of getting rid of money. I thought it's a tiny little assumption, and what the hell. And I have to admit that the more I'm working on this, I see that really money is a real limitation. It really breaks your, many problems that you're interested in, you cannot actually take into account. And I will talk about this in this talk. I will talk about one very, very simple constraint that you see all the time in real life that simply does not fall into the quasi-linear model. You cannot just express it with money that everything is simply linear in the money. So money will be in it, But it's not that you can always just add the money to the value that you get from the rest. And before I want to get into it, actually this is a problem that actually started by some real problem, and I thought to tell you about the real problem. Not that the solution would have anything to talk about the original problem. It would be a nice little theory, but at least I thought that the motivation would be, I should talk about. And of course I work now in Google, which as you know is an advertising company. And basically what they do is they sell ads. So they can sell ads, what's called AdWords. So these are little ads here, little text ads next to your search results. They also sell what's called display ads. There's big ads, which can be on any web page, and you can have various things there, like pictures. And by the way, actually, Google also sells TV ads, and actually now it's just announced that it will stop selling radio ads. But it sells all kinds of ads. Okay? So what do I mean it sells all kinds of ads? That's very important. So from the point of view of the advertising world, basically what you sell is this area, and this area, and this area, and this area, and these 30 seconds on the TV at this time and this station. That's what you sell. Everything else is sort of just a ploy to get people to watch your ad. So the way that people work with Google and the AdWords, basically, Google actually does an auction for every little ad spot that it has. So to know which guy gets his ad to show here or there, basically there's a little auction done every time someone out there is actually looking at the ads. And if you're an advertiser and you want to say, I want my ad to appear there, this is basically what you need to specify. So you first need to specify where, of course, first you have to give, this is my ad, okay? It's text or a picture or a video clip if it's a TV ad. Then you have to say, where do you want your ad to appear? So it can be on web pages in a certain TV show in time, or you can, of course, there can be lots of complication how convenient it is to express where you want your ad to appear, okay? But at the end, I want it to be here, 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 there. These are all the places that I'm interested in. Then you have to say, how much are you bidding for it? How much am I willing to pay for my ad to appear there? And again, the way that you count how you can specify how much you're willing to pay, you can specify it either per ad, or per 1,000 viewers, or per clicks, or per action, or various other ways. At the end, it's just, I'm willing to pay X if my ad actually wins and gets that place. The third thing that you need to specify is a total budget. So this auction is actually runs on every single time there is someone watching a certain web page, there is some kind of unit that's being ad slot that's being sold. You will win some of them, you will lose some of them. At the end, there's also your budget. What is the total amount that you're willing to pay for all of your wins in a certain day or week or period or whatever? So, and this is your input. And once you enter this input, which can be simple or complicated because each one of these can be specified in various, convenient, less convenient or more convenient ways, then simply Google runs a sequence of options. Each time somebody wins in some. And the question is, how are we looking at these things? What's happening there? So if you look at the target and the bid, that's very easy to understand what's going on. That directly corresponds to the valuation in theoretical terms. You're saying, how much do I value if I get this item? That's a number. This is worth $7 to me if I get this spot or that spot. And by the way, in this context, it's very simple. If I get a collection of spots, it's just the sum of values. That's what I'm interested in. But the problem is what happens in the budget. The budget is not something that you can simply push into the valuation. It doesn't say how much something is worth for you, but rather how much you're willing to pay for it, which is something completely different. Okay? So if I'm saying my budget is $1,000, it does not mean that if as many spots as you give me, it's only worth $1,000 to me. No, I'm still happy to get more and more, and I may prefer these spots over that spot and so on, but I simply cannot pay more than $1,000. So the budget simply does not fall into the quasi-linear model. It's not linear on something about your valuation, but rather about how much you pay. Now, so actually it's quite of a mystery. What the hell are these budgets, if you want to look at it? So that's, of course, a very obvious from any business point of view, and that's the first thing. And what do these budgets mean? Why do advertisers use any kind of budgets? So if you try, there's no real good answer to that, but if you start looking into it, so the first kind of distinction that people make is between, there are basically two kinds of advertisers. The real truth is, of course, everyone is somewhere in the middle of a spectrum, but the direct response advertisers are the ones that basically want you to do something now and buy something now. So if you see this kind of ad, they really want you to click and buy gold now on the internet. Okay? Now, these advertisers, they are basically usually quite quasi-linear because they know exactly how much money they'll make from you. They know from people who come to their website, 2% actually make a buy, and on those that make a buy, on the average, they make $30 net revenue. And so they know exactly how much they're willing to pay for an average customer to come through their website. And they will basically bid their value up to that level and no more than that. And from their point of view, this is basically like a money pump. The more people they get to their site, the better it is, and their budget should be basically infinite. And for all practical purposes, it is infinite. Because usually whatever limits they have on their business, I don't know, the total amount of gold that they can buy or something like that, is much larger than what they can actually sell. So these guys really do not care about the budgets. But then there are other, and by the way, but then there are other kinds of advertisers. Basically, in general, want to give you some kind of, fuzzy feeling. Coke is good, it will make you young and happy and lovable and loving. And they're not making immediate money out of it, but somehow it's changing your brain and you'll keep buying Coke for the rest of your life. And these guys, they cannot measure. So you would think that even these guys would know how to value, how much is it worth for me, Coca-Cola, that you watch my ad, but they don't. They simply do not. They have no idea. But what they do have an idea, and this is a fact of life, they know what their budget is. They now have $5,000 per day to advertise on the internet or on this kind of TV radio station. And why is it $5,000? What does it really represent? It's less than clear. It's probably something about the way they're managed rather than anything real in some economic terms, but it's not completely clear. But what cannot be denied is that the reality of life for these advertising, for Google, for example, and in many other scenarios, that the budgets are extremely real. These kinds of Coca-Cola companies have no idea what their valuation should be. That seems like a totally abstract, meaningless thing for them. But they know what their budget is, and we have to take this into account. Okay, so what was happening previously about budgets in the world of auctions? So first of all, one thing that I should say explicitly, that auctions are actually an exception within economics, but in the rest of economics, for example, in the markets and the Bro model and so on, budgets are an integral part from day one in the model. Okay? So, but only in auction theory that is not the case. And the reason is because it doesn't really work so well, things are more difficult. So there are a few works in economics for economists. Basically, they look at standard kind of auctions, first price, second price, and see what happens when there are budgets there. Do you get more revenue, less revenue, comparing them, things like that. Lately, there have been a bunch of works coming from computer scientists working on auctions, and not surprisingly, we're talking about people from Microsoft, Google, and Yahoo, that basically actually ask exactly this question. I have a bunch of items to sell. There is a value for each item and a total budget. How do I allocate it correctly? So the guys from Microsoft, Borg et al., they designed auctions with good revenue properties using some kind of randomized auction. Feldman et al., that's a group from Google, actually designed AdWords auctions with some complications, but with certain non-standard model. And there's work by Zoe Abrams that actually considered what kind of revenues do you get in this setting. So, there is some work here. And of course, there are even more guys actually talking with computational issues, with purely computational issues. The works that I have described here are the ones that actually take what's called incentives into account, so they really look at this as an auction problem and not just a kind of combinatorial optimization problem, which there are still other problems, especially if you want some kind of online models. Okay. So now that was like this is where we came from. So now what is our model and what are we doing? So the model is very simple, what's called a multi-unit auction. Basically, there are n units for sale, and they're identical to each other. Each bidder has a value V for each unit. Okay? And also, each bidder has a budget V for everything that he can spend altogether. So now the utility of an advertiser, so the utility being what he aims to optimize, when he acts, he will act in a way that optimizes this. It's very simple. If what he pays is at most his budget, then we're simply in the usual quasi-linear setting. Then it's the amount that he makes. So we got X units. Each one of them is worth V. So his value he gets X times V from the units that he got, minus the payments that he gets, that he pays. However, he cannot pay in any case more than his budget. Okay, so this is a restriction. This is where the quasi-linearity breaks. It's exactly this point. Okay. And we'll also talk, so we'll try to work together with the finite model, where you have a finite number of elements, n, for example, 3, and the limit case, where you have an enormous amount of items, which will just treat m as 1, but infinitely indivisible. So this is like having some kind of a continuum of the items, but basically the large m basically does converge to this case. Okay, and of course, the interesting case is where the budget comes into play. Okay, so for example, that you cannot win everything, because if you won everything, then you would be over budget. Okay, so one question is, the first question is, so usually in auctions, it's pretty clear, at least intuitively, what kind of things we want to optimize. So there are usually two possibilities. One of them, okay, I want to optimize my revenue as an auctioneer. Okay. And the other, this is like the question that the guy from Microsoft asked in the previous one. And the other question is, I want to optimize social welfare, what's called. I want to optimize, just get the allocations that's optimal for everyone. Okay. And this is the question that I'm interested in now. Okay. But the point is, it's not completely clear even this. So suppose I don't care about my own revenue at all. I just want to find the allocation that's best for everyone together. What does it mean in this situation? You can't just give all items to the guy, to the bidder with highest V, with highest value, because that ignores the budgets completely. So what does it exactly even mean to allocate it in the most efficient way? Okay? It's not clear. So, with the lack of clarity, there's one thing that obviously we need to do, and this is what's called getting a Pareto efficient allocation. So while it's not clear what is the best solution, okay, it's clear what is definitely a bad solution. Okay? So a bad solution is a solution which you can completely improve it. So let's look at an allocation XI/PI. So each bidder I gets XI units of the item and pays PI dollars. Okay? And let's see what would a completely better allocation from that be. So a different allocation with primes is strictly better than our allocation if it's better for everyone. So first of all, every bidder is happier with a prime allocation than with a non-prime allocation. Second of all, the auctioneer itself, the total number, the amount that they pay, is more in the prime allocation than the non-prime allocation. And one of these equalities is actually strict. Okay? So if you can actually improve things for everyone, for at least one person strictly and for the others at least not hurting them, then definitely you're not in a good situation. Okay? And the usual requirement is that allocation is Pareto optimal if there's no other feasible allocation which is better in this sense. So this is obviously the weakest requirement of efficiency you can look for. So if you're not efficient this way, you're definitely does not make sense. Now in this situation, the Pareto efficiency basically says that two bidders cannot basically exchange some money for a good and both of them be happier than that. Okay, this is not true always in general, but in this situation is true. So what does it mean? That if I have a value that's for a unit that's higher than your value, then it should be, then of course what we could do, I could, and you got 1 unit even 1 unit, I would want to take that unit from you and pay you some kind of sum of money that's less than what it's worth for me and more than what it's worth for you. Okay? So the only reason why I could not do that if my budget was exhausted already. Okay? So that's basically the criteria when you can see that something is parallel efficient. Okay.
So if it's Pareto, everything is allocated?
Yes, in particular, if it's Pareto, everything is allocated. Yeah, so
can't it be that the prices are too high for everybody and just only Pareto is not to buy anything?
No, we get to set the prices. You can actually give prices of 0. Okay? Part of the allocation is prices.
There's no preset price. Everyone makes an offer.
We are not
Yeah. Yeah, and maybe I'm lying a little bit with values that are 0. If a unit is not worth nothing to anyone, then it's not exactly true. But okay. Okay. So the first question is, I'm trying to tell you what is the allocation that I'm trying to get. Very minimal requirement. The second question is, how am I taking into account the fact that we're talking about different people who have private values, and what do they do? So I'm going to design an auction, basically. So what's an auction? I'm going to design some kind of protocol that, each one of the participants has to tell me something, and then I allocate according to a certain rule. That specifies what I, as auctioneer, do. But what do the bidders do? Okay? So of course, the whole point of this auction theory kind of exercise is that you specify the rules, and then each one of the players participates in the way that they want. And the basic assumption in auction theory is that while they can do whatever they want, as opposed to what we do in computer science, we maybe assume that they're malicious or something like that, here we just assume that they are rational. They will do what's best for them. Okay? Okay, so what is best for them? That's not a psychological statement, but rather a completely mathematical one. They will work in a way that optimizes their utility as stated. Okay? So that completely specifies what each one of them will do, but of course there's an interaction there. So there could be some kind of a game, and we should look at an equilibrium. But here's the strongest notion that's usually used, and that's, we say that an auction is incentive compatible if all bidders always maximize their utility by simply reporting their private information truthfully. Okay? So always means whatever the other bidders are doing, so they don't have to play this game with the other bidders, because whatever the other bidders are doing or saying, they want to just tell us the truth. Okay? And this is a situation. So you manage to design an auction with rules that actually make it worthwhile to everyone, just tell you how much they value it, what is their V and what is their B, then you're happy. Then they will presumably just tell you your V and your B, and you'll be able to calculate whatever you want to calculate. And now, so I don't want to give a whole introduction to this whole idea of incentives, but one thing that I want to say that you can obviously think about other kind of mechanisms where people don't just tell you their input, but react in some kind of strategic way, which is not true. And then you analyze what happens when you take into account all the strategic interaction between all the different players. And then you look at the outcome and say, okay, I want that outcome to be good, let's say Pareto optimal. Okay? Now, what's called the revelation principle shows basically that you can simulate any kind of complex protocol, indirect protocol like that, simply by a direct protocol where they just need to tell you their input, and you do the calculation for them simply by simulation. You take into account, you simulate whatever their strategy is, and you just do it for them. Okay? And it works. So this is really the idea that we're looking at incentive compatibility. This is really basically without loss of generality, as long as we're taking into account what happens after strategic interaction of all the players. So our main theorem is the following, that you can't do it. It's an impossibility result. So as long as you have more than a single unit, okay, so if you have one item and there's a value in the budget, you can sell it in an incentive compatible way. You just take the minimum of the budget and the value, and that works. But as long as there are more than one, and more than one includes, the infinity or whatever, then you cannot do it. You cannot do it as long as we're talking, we're not bypassing the budgets by actually, paying people lots of money or anything like that, as long as what's called, you never pay more than what you got is worth for you, and you never get money. Okay, so these are standard things which actually make sure that we're not cheating and ignoring the budget in some way. So as long as you're what's called individual rationality, that means you don't pay more than what you get, and no positive transfer. I don't pay to you money in order for you to get even more stuff, then you simply cannot do it. Now, while there is that's a basic result showing that the thing itself is hopeless, we do have positive results. And basically, the positive results say that if the BIs, the budgets, are public knowledge, so the whole impossibility is in the situation where each one has a private value V and a private budget B, and we have to do something that's incentive compatible for these two inputs, secret inputs. Once the budgets are public knowledge, then we do find incentive compatible mechanisms, and they're weird. So they're really strange, not like any other option that I've seen before. And I mean, simple, but weird. And these are not bad in terms of revenue. They're, the revenue is the right kind of things. And actually, the way that we actually prove the possibility result is because these weird auctions are unique. There's only these are the only auctions that are incentive compatible and Pareto optimal, at least for the case of two bidders. And once we know that they're unique, then basically the impossibility for the general thing just follows because they're unique, and what happens depends on the budget, and for different budget you must do different things, and basically that dies. So before I actually show you the general, try to derive it, here's a solution. Here's like one of the unique auctions that I was talking about. So here's a unique auction where you have two bidders. Alice has a budget of 1, and Bob is not budget limited at all. Okay, so this is a situation when one of the players has a budget and the other player has no budget limit, simply infinity. So Alice has a budget of 1, and Bob has an infinite budget.
Coca-Cola versus the gold guy.
Yes, for example, yes. Okay, so then there are two situations. The first situation is if the values are less than 1. Okay, I'm talking about the situation where the number of units is a continuum. Okay, so it's infinite, and so I'm looking at it as 1 unit. So basically, if you get a quarter of the good, you play V over 4. So you need to somehow shift something times V should be comparable to V, but this something is now going to be less than 1 rather than a huge number. Okay, so it's a fraction. So if the value is less than 1, if the minimum of the values is less than 1, it means really the budget doesn't come into play at all. Because, you have enough budget, even Alice has enough budget to buy everything, or at least according to the cheaper guy, and basically what you do is what's called the second price auction. You simply give everything to one player, to the player with higher value, and the amount that he pays is the standard classic second price. The interesting thing is what happens when the budget do come into account, and then there are two possibilities. One of them is that Alice has a higher V, and the other is that Bob has a higher V. So if Bob has a higher value than Alice, so not only does he have an infinite budget, but also his value is larger, then Bob gets everything. So Alice that has low value and low budget gets nothing. But the really strange thing is how much do we want Bob to pay? And what he pays is 1 plus the natural logarithm of the value of Alice. Okay? And this has to be it. On the other hand, if Alice has the highest value, then what happens is as follows. So Alice basically gets to buy stuff at a price per unit of value determined by Bob's value, VP. So basically she pays everything, all that she's got, her budget, and the amount that she gets is the correct fraction as this price. Okay, so she pays 1 and gets a 1 over V of Bob fraction, and Bob gets the rest, and pays for it the natural logarithm of his own value. Okay? So this is the result, and now I'll try to slowly derive and show you why this has to be the only thing that can be done.
Who's paying more? Bob or Alice?
We're in a situation where the value of Bob, the value of Bob is more than 1, because, right? But it can pay less. I mean, it's possible that Bob is paying much less. I mean, specifically because maybe he only gets just a tiny little amount, right?
Can be more, can be less. No?
Can be more, can be less, yes.
Above or below?
Yeah. Okay, so I want to start with what's called the market equilibrium, the classic economic way we would approach this kind of question, and then see what's wrong with it, and then just slightly change it. Okay? So let's do a supply-demand kind of analysis. So what are people wanting? So suppose that we knew the price was P. How many units would Alice want? How many units would Bob want? What would be the supply be? What would the demand be? How would we allocate it? Let's do this exercise. And then we'll fix. Okay? So let's see what is the demand of bidder I at a certain price. Well, basically he has a budget B, I. He has a budget BI. The price per unit is P. So his demand would be BI over B units. But this is, of course, as long as the price is less than its value, because if the price is more than its value, he doesn't want anything. Okay? This will be the demand of a certain bidder. So then we can get basically the demand of all the different bidders, and compare that to the supply, which is M units. And you can do some kind of analysis, what would be the equilibrium, basically solve the equation of demand equals supply, where this is the form of the demand. And you can see that the price is basically, you take everyone, or we take the budget of everyone that's winning. In a second I'll say who is everyone that's winning. You take the budget of everyone, and basically this amount of money has to basically be split into all the units that are being sold. And what you get is basically your proportion of the total budget. Now, this is true as long as these guys actually are willing to pay this amount of money at this price. Okay? So the sum is not over all the possible players, but only with those that have a value that's high enough. And high enough, of course, now the problem is that P also determines what are you summing over, so you just need to basically find the right P that, if you look at the V's, which actually sum only over them, you still get the right quality. Okay? So the nice way to actually think about this, and by the way, like any market equilibrium, it's Pareto efficient. Okay? So it's the way to look at it, because it's not completely clear how you do this, how you do this calculation of finding the P, which also depends on the set of V's that are larger than the P itself. The way you can look at it is actually as an ascending auction. If you take the price and you slowly increase it, and each point you actually say, you ask the people, everyone, how many units do you want? And if they want too many units, you keep on increasing the price until at some point you get into equality. Okay? And that would work, and I actually want to give an example. Suppose we have, I'm running a market here. Suppose we have just two bidders and 200 items. Suppose that their values are large. Okay, so I don't want to actually put this as an example. And one guy has, Alice has a $500 budget, Bob has $1,500 budget. So we start with price of 1, at which point Alice says, okay, I want everything, because it's only cost me $200, which is less than my budget. Bob wants everything. Total demand is 400. Supply is 200. The price needs to go up. So with 2, still everyone wants everything. At 3, things change a bit, because at price of $3 per unit, Alice does not want everything, because she can't pay for it, but she wants 500 over 3. And of course, we're talking about integer units, so she really wants 166 rather than 166.6. Okay? But still, the total demand is more than what we have available, so the price needs to go up. At 4, Alice only wants 125. At 5, only 100. I'm jumping. Let's say at 8, well, Alice wants 500 over 8, and Bob wants 1,500 over 8, and the price is still too low. At 9, the price is still too low. Luckily enough, at 10, actually, Alice only wants 50 units, Bob only wants 150 units. Together, bingo, this is exactly the same. Actually, this would happen just slightly before 10, at something like 9.999. Still, Alice would only want 50 because 51 would be too much, and Bob would want 150. So really, the equilibrium would be something like 9.99. No, not the equilibrium, but this auction would give you something like 9.99. Okay? So at this point, this is the allocation that we get. She gets 50 units. She pays $500, slightly less than that, really. 50 times 99.9, and so on. And that's the auction. Okay? So now the question is this incentive, okay, so the outcome is Pareto optimal. There's no better way to allocate stuff. But is this incentive compatible? Is there something better that they can do? Okay. So a few things about this kind kind of thing. First of all, the ascending auction does reach an equilibrium price when it stops. You need to be careful. At a certain point, bidders may drop completely out, and then at the exact point that they drop, it may change between too little to too much, but any point in the middle is good if you wish, and that will be an equilibrium. And it's always Pareto optimal. But the point is, this is not incentive compatible. So the way you as a participant could improve your luck, get a better utility, is what's called the classic thing of demand reduction. If you are willing to take less items, then of course you will not be as happy at getting more items, but that could decrease the price significantly, so you'd get a total gain. Okay? So for example, suppose so far I didn't talk at all about what is the valuations of the players, but suppose that Bob's valuation is 11. So you can see it makes really little money, really little gain from it, because the price now is 10. But he is in his power, is completely within his power to make sure that the auction stops at a price of 5, for example. For example, if he says, no, I'm not willing to pay more than 5, then at that point, at 5, Alice will only be able to buy 100 units, because that's her budget allows, and he will get the other 100 units at the price of 5, so obviously this is much better than really just playing normal. So if you are willing to be slightly less greedy, you'll get a better deal. This is very well known. Now, but still, this does have some nice properties. So basically, if either the budgets don't come into play or the values don't come into play, that is, the values are either very low or very high compared to the budgets, then this is incentive compatible. So really the only way you could gain is by this kind of budget, by demand reduction. But can we get something that works completely? So what is wrong with this kind of auction? What makes the non-incentive compatibility? So basically what happens is that, then it's a little bit difficult thing, but I think part of the idea of this whole auction game is that I shouldn't be paying as much as, to the point that it got, but I should be paying basically the harm that I cause to others. Okay? So the amount that I should be paying is the minimum that was needed to buy, and usually the minimum that is needed to buy is what would be the other option. What am I causing others not to get? And this should be the kind of logic behind it. And indeed, Osabo actually suggested an auction for the multi-unit case without budgets that is just slightly different from this ascending auction, and actually exactly tries to capture this idea. And Osabo suggested the following idea. So indeed, as before, you increase the price as long as the demand is more than the supply. Now, as you increase the price, the players will demand less and less units, will want less and less, because, for example, for whatever reason. And what I look at as a bidder, when can I be sure that I'll get the unit? So when can I be sure that I get the unit? Well, if all the other bidders together want at most m minus x units at this price, then it sure certainly that I get at least x units in this auction. The price will only go higher, maybe but at least x units I will be willing to get at this price. And the idea is that what I should be paying for a unit is the lowest price at which I what's called clinched it. So I clinch the unit if everyone else does not want it anymore. So I keep on rising, and as the prices go up, other bidders want less and less items. I keep clinching units, and each time I clinch a unit, that determines the price for this unit. So I get the first unit for a low price, the second unit for a slightly higher price, and so on, until I say, no, I don't want any more units. That's what Osabo suggested. And in the usual model of auctions, he actually shows that this is actually what's called the VCG prices. So this is incentive compatible, just a different way to actually view the usual what's called VCG prices, which are incentive compatible in terms of an ascending auction. So what we actually observe is that actually this also works very well once you have budgets. Now there's a delicate thing that you have to know. In terms of in the usual say, if you don't have budgets, when I say what is the demand of the other guys, that's completely determined to begin with. It's not, you can actually write a formula that's saying what would be the demand of all of the other guys at price 7. Because they have their budget divided by 7, very simple, maximum with a value, very simple. In our situation, their demand actually depends on how much money they spent so far for the item that they clinched already. So there's some kind of algorithmic kind of thing going on here, where you clinch a bunch of units which actually determines the price that you pay for them, and that determines the price that you already paid, determines the budgets that your demand ongoing. But still, at least if we look at it algorithmically, we just say, okay, you just run the algorithm, you keep on having this. So if I've clinched units, I look at my remaining budget, so my original budget minus the sum of all the prices of the units that I've clinched, divided by the current price, because I know that the new units that I get are going to be at price P. Okay, so that's basically the algorithm, the options that we have. You basically run this ascending price, but you keep on track when did I actually win a unit and how much did I pay. And the only thing that I'm really cheating here is how to exactly handle ties, where two guys drop together, one of them because budget, one of them because value, but that's detailed. So let me run an example. So suppose I have 3 items for sale and 2 bidders. Alice has a budget of 12, Bob has a budget of 14, and again, let's assume that the values are high. So let's see what happens. At price of 1, Alice still has everything remaining, she hasn't clipped anything, so she wants 3 units. Bob still has 14 available, and he also wants 3 units at price of 1. At price of 2, the same thing. Still Alice can pay for all 3 units, same can Bob, same thing at 3, same thing at 4. Now when do things change? Well, when we go slightly above 4, to 4 plus epsilon, okay, at this point Alice does not want all 3 items. Okay? So at 4 per epsilon, Alice does not want, so her demand goes down to 2. While Bob still wants all the 3 because his budget is 14. At this point, Bob clinches an item at the price of 4. Okay? So once he clinches an item at the price of 4, his remaining budget goes down to 10 because he already paid 4. And his remaining budget hasn't changed. And they keep on going. Okay? So again at 5, still Bob wants both items, but now when we go up to 5 plus epsilon, now we will only want 1 more item. Okay? At that point, Alice clinches this item for a price of 5. And we keep on going. So at 6 now, what I should say here in 6, Bob has $10 remaining, Alice has $7 remaining, the price is 6, both of them want it, both of them have clinched 1 item, Bob for the price of 5, Alice for the price of 4. Okay? So at 7, plus epsilon, Alice does not want an item at all, so Bob gets a second item for a price of 7. Okay? So the total outcome is that Alice gets 1 item for $5, Bob gets both items for $11, and the theorem is that this is it. Okay, so what can we say about this adaptive clinching option? So the first point is it incentive compatible? Should I always just do just play, do the right thing, just play, report my current value and my correct value and budget, and let the algorithm run correctly? Okay. And the answer is no. Why not? How can you gain? So the only way you can gain is basically so the way you gain is indirectly. If you exhaust your opponent's budget faster, then you will clinch units earlier and pay less for them. So the way to gain is to report basically higher budgets than you have. By this, we keep on reporting higher demands, making your opponent win items later and pay for them more, and hence exhaust their budget. So actually this is something that you can do, and it's very easy to show that. However, what can be shown is that if you can't play with your budget, if the budgets are completely known, so in particular, the budget is completely known means that the demand at each point is completely known. Okay? The only question you have is whether you drop out of the budget of the auction because you've reached your value and then your demand goes to 0. And if you haven't dropped out, the demand is completely known. Then it is incentive compatible. And the reason is pretty simple actually. Well, the only thing you can basically do is decide whether to drop out of the auction or not. Any item that you win after a certain price, you will only pay for it more than this price, so there's no reason whatsoever to remain in the budget when it reached your value. And there's no reason to drop too early because you can always drop later and keep on getting items before you drop. So this is actually quite easy to see why this is incentive compatible. And also it's not difficult to show that it's Pareto optimal. Basically, once you drop, you cannot, it's exactly the point that you can't get anything from anyone else either. What's more complicated is showing that this is unique, but again, this is actually, the proof here is somewhat unusual in the field. Basically, you show that the price for the first item that it's auction sales, it has to be. You can't sell for less than that, and then you can simply run induction. But that's a delicate part. Okay, since I don't have time, let me skip the revenue, which is good. And let's go back to the example that I showed you, and let's see how it basically is implied by the previous auction when I run it like in a continuous dynamic process rather than, this thing. Okay? So if you remember, this was the auction that I showed you that, Alice has a budget of 1, Bob doesn't have a budget limit. And we said that if the values are low, you do a second price, and afterwards, basically the interesting thing is what you pay the logarithm of Alice. And here's the logic. Let's see what happens when we run our auction, or Osibel's auction, in this setting. As the price increases from 0 to 1, assuming that the values are high enough, they're above 1, basically Alice wants everything and Bob wants everything. Because the value is more than 1, and their budget is, even Alice's budget is 1, so she can buy everything. So nothing is clinched until the price reaches 1. Now, when the price increases from V to the minimum, to the lowest price of V Alice and V Bob, that is at this point still both of them want it. Bob wants everything because he has no budget limit. Alice can only pay for 1 over P. Okay? So how much does bidder B, how much can he have clinched until price P? Well, basically at P, Alice only wants 1 over P, so bidder up to P, Bob clinched 1 minus 1 over P units. How much does he pay for it? Well, we said that what he clinched at a certain price, a certain price P, he has to pay basically P for that little unit. So to compute what he paid, we basically need to integrate the amount that he clinched at price P, which is a derivative of this function C. This is the amount that he clinched at price P, times the price P that he paid for that amount. And you simply integrate that from 1 to P. And if you integrate it, that is log P, and that's what you get. And then, at that point, you actually allocate the bunch to Bob, this price. And then at that point, either Bob or Alice goes away, and the other guy gets everything for the price remaining. So this is what you have to do. Okay, so I think I'll stop here. Just say that, in general, I think that budgets can be dealt with in auction theory. It's a bit cumbersome. Not always the most natural or more useful practically auctions, but I still think that there are things to be done there. And two specific questions there. One of them, we always wanted exact incentive compatibility and shows that you can't do something unless a budget or public knowledge. So of course we can weaken the requirement to some kind of approximation or weaken notion of incentive compatibility until we get something positive. The other question, of course, we use budget in simply multi-unit auctions, basically auctions where all items were the same, identical. Of course, we can talk about combinatorial auctions where the different units are different, which is a very large area, but take budgets into account, and it's more complicated, of course, than this. So, thank you.
So thanks for the invitation. I will talk about the connection between the primal dual method and online algorithms. Online algorithms and competitive analysis. So just a quick recap, what's an online algorithm and what is the competitive analysis. So in an online algorithm, the input arrives, we don't get the whole input right away. We get it in pieces, each piece is referred to as a request, and the online algorithm is expected to respond to each request, and decisions cannot be taken back. So once an online algorithm makes a decision, that's it. The algorithm cannot change it later on. And the competitive factor is a very common measure for evaluating the performance of an online algorithm. And the idea is we are going to, for a given sequence of requests, we're going to compare the performance of the online algorithm to an optimal offline algorithm that knows in advance the set of requests. And the ratio is going to be the competitive factor per request sequence. And if we can bound this ratio for every request sequence, then this ratio is going to be defined to be the competitive factor of the online algorithm. And you can think of it as a normalization. The performance of the offline algorithm, the optimal offline algorithm, is a normalization factor on the performance of the online algorithm. So let's think about an abstract online problem where we have variables, x1, x2, and so on. We have some objective function. Let's say we want to minimize a linear objective function. And now we start getting the constraints. Now, the constraints are arrive one by one, and this is the first, second constraint, third constraint, and so on. And in this talk, I'm going to restrict myself to the case where all the numbers in all the coefficients in the matrix and in the objective function are all non-negative, but it's not necessarily the case. And now what happens what are we required to do for every constraint that we get? So first, when we get a new constraint, we need to satisfy the constraint, which means that we need to decide on values for the variables that appear in the constraint, so that, let's say when we get the first one, we have to set values to x1, x3, x6, so on, so that the value of the constraint is going to be at least 3. And now we have to be consistent with our previous settings to the variables, which in this case means that the settings, the values that we assign to the variables have to be monotone. So we cannot decrease a variable. If we are allowed to both increase or decrease, then the online nature is really meaningless. So we're only allowed to increase values of variables in this setting. So let's see, and of course the final goal is to minimize the given objective function, which is given in advance. So the objective function is known throughout the execution of the online algorithm. So let's see a concrete example. So we want to minimize sum of x1 plus x2 and so on. And the first constraint that we get is just the sum of all the xi is bigger than or equal to 1. Well, what can we do in this case? The smartest thing to do seems to be just set all variables to be 1 over n, since we have no other information, and then the constraint is satisfied. Well, then we get another constraint, which is x2 plus x3 and so on, plus xn is bigger than or equal to 1. Unfortunately, the values that we set previously are not high enough to satisfy also the second constraint. So we'll just increase x2 up to xn, the variables that we currently have, we'll just increase them to 1 over n minus 1 and satisfy the constraint this way. This goes on. Each time we just increase the variables which are in the current constraint. And eventually we only have xn, and we have no choice but to set xn to be equal to 1. So had we known that this is the set of constraints, what could we have done? Well, we could have set xn to be 1, and that would have satisfied all the constraints, and then the value of the objective function is 1. Unfortunately, what we did, we basically get the harmonic sequence for all the variables in the constraint. So xn is 1, xn minus 1 is half, and so on. So we get the harmonic sequence, and there's a logarithmic gap between the offline and online. Now, this is not precisely a lower bound argument for the online case, but it's very easy to make it also into a lower bound argument. So this just comes to show that in the online setting, we cannot get better than a logarithmic factor. Now, what can we do with this very abstract setting? So it turns out that using linear programming formulation, what we saw before in the previous slide is just an example of an LP. Using an LP, we can describe a very large family of problems that have been studied extensively in the online literature, and we can come up with a more or less uniform algorithm, family of algorithms that is applicable to this very large family of problems, starting from ski rental, AdWord auctions, congestion minimization, and I won't read the whole list here. So let's see a few examples. So it's difficult not to mention the ski rental problem when talking about an online problem. So a skier goes skiing, buying the equipment, the skis, costs B, renting costs $1. What should he do? So the online nature of the problem is that he doesn't know how many days in advance. He doesn't know how many days he's going to ski. Every day he's being told, okay, today you're going to ski, and then one day abruptly his ski vacation is over. Now, what should he do? Buy or rent? Deterministically, there isn't really much to be done. You just rent for the first B days, and then you buy the equipment, and of course on that day the cruel adversary is going to terminate the vacation. And in this case the competitive factor is 2, because an optimal offline algorithm would also have to pay B, and this is and it's easy to see that this is an optimal algorithm. How can we formulate this problem as an LP? So let's say X denotes whether we buy or don't buy the equipment, so it's 0 or 1, and ZI indicates the event that we rent the skis on the ith day. So the objective function is we want to minimize B times X plus the sum of the ZIs. Now, what is the constraint? The constraint is that on every day we need to either buy or rent. So on every day, X plus ZI has to be bigger than or equal to 1. And we're still in the 0, 1 world. Now, let's give up the integrality constraint, and let's think about this problem in the fractional setting. So now we are allowed to buy only part of the equipment, but it has to be monotonically increasing. If we, on a certain day, up to a certain day, we've bought 1/3 of the equipment, we can't sell back a portion of it to the store. So, so this is our covering. This is our LP, and you can see that the constraints arrive. The constraints are not known to us in advance. Only the objective function. The constraints arrive one by one, and every day we get a new constraint. We have to satisfy it, and again we have as I said, we have the monotonicity requirement. What is the dual problem? So the dual problem, it's a packing problem. We have a variable yi for every day that we ski. We want to maximize the sum of the yi's, and each yi is less than or equal to 1. And we have a constraint that the sum of the yi's is no more than b. Okay, so let's see a simple fractional algorithm for this problem. So initially, of course, x is 0. We haven't done anything. As long as x is less than 1, so we still haven't bought the equipment completely, then first of all, we want to be feasible. So if x has some fractional value between 0 and 1, we'll rent the rest. So 0 is equal to 1 minus x. And since, like in the deterministic case, we waited b days until we bought the equipment. Here, every day that we ski, we buy a bit more of the equipment. So we multiply x by something which is inversely proportional to the cost of the equipment. And we set the dual variable yi to be 1. Okay, now to analyze the competitive factor of this algorithm, what do we need to do? Well, ideally, we want the primal solution that we generate to be feasible. We want the dual solution to be feasible. And if we can bound the ratio between the primal increase and the dual increase in every iteration, in this case, show that it's 1 plus 1 over c, where c is some parameter that we'll fix later, then the algorithm is going to be 1 plus 1 over c competitive. So let's go quickly over the proof. It's very simple. The primal solution is feasible because we make sure that zi is equal to 1 minus x, so we have that for free. Let's see why the ratio between the primal increase and the dual increase is no more than 1 plus 1 over c. So c, just the parameter c comes in here, so the function by which we update x, we multiply x by 1 plus 1 over each new day that we ski, we multiply x by 1 plus 1 over b plus this additive term which contains c, which we're going to optimize. We're going to optimize c. So what happens here? So so the dual changes by 1 because we set yi to be equal to 1, and the dual objective function is just sigma yi. So the dual increases by 1. What's the change in the primal? The change in the primal is, for the change in x, delta x, we have to pay b, plus the value of the variable zi, and when you do the calculation, that magically turns out to be 1 plus 1 over c. So we're happy with that. What about the constraint? So now we have to show dual feasibility. So each variable yi is set to 1, and that's fine. That makes it feasible. But we have to make sure that sigma yi is less than or equal to b. In other words, we want to make sure that after b days, we're going to buy the equipment in its completely. Otherwise, we have to, at least according to this algorithm, we have to keep on increasing, setting the next yi's to be also equal to 1, and then the sum will exceed b. Well, the increments of x define a geometric sequence which starts from 1 over cb. Just look at this update rule. Then a1, the geometric sequence starts from 1 over cb, and we multiply each time by 1 plus 1 over b. So x, the variable x, is really a sum of a geometric sequence. And when we do the calculation, and we want to make sure that this sum after b days is equal to 1, and that gives us an upper bound on c, which is equal to 1 plus 1 over b to the power of b. And when b is large enough, goes to infinity, then the competitive factor of 1 plus 1 over c is equal to e over e minus 1. So what we see here is a fractional algorithm. So by allowing the algorithm to be fractional, we're able to break the trivial upper bound, deterministic upper bound of 2, and get an e over e minus 1 competitive factor for the fractional case. It's really easy to make, in this case, to turn it also, to take the deterministic fractional algorithm and make it turn it into a randomized integral algorithm. All we need to do is just write the increments of x. Let's call them x1, x2, x3, and so on. And the algorithm is just going to choose in advance, before we run the algorithm, we're just going to choose a value between 0 and 1 uniformly in random. And we can think of these xi's as bins. So in the randomized case, the question is, on which day are we going to buy the equipment? And we're going to buy the equipment on the day, D is the random variable that we're choosing between 0 and 1. So we're going to buy the equipment on the day that corresponds to the bin in which D fell, into which D fell. And we're going to rent the equipment up to that day. So clearly the probability of buying on the ith day is xi, and it's not hard to show that the probability of renting is also on the ith day is also at most zi. So the expected cost of this randomized algorithm is the same as the deterministic cost of the fractional algorithm, and we get that the randomized competitiveness of this algorithm is e over e minus 1. Now, this by itself it's not a new result. It's actually known from the early 90s, I think. It was, if I'm not mistaken, it was first shown in a paper by Anna Carlin and a few other co-authors, but they didn't get it in using this method. They did it in some other way. Okay, so the C problem is a very specialized problem. The coefficients. So first of all, the constraint matrix in the LP has coefficients which are 0, 1, and we'll see later that actually these ideas can extend to arbitrary matrices with 0, 1. But before we do that, let's look at another example, but this time I want to look at a packing problem. So ski is an example of a covering LP. So in a covering LP, we want to minimize an objective function, and all the constraints are bigger than or equal to. Again, all the coefficients in the matrix have to be 0, 1. We don't have negative numbers in the constraints. In a packing problem, we want to maximize an objective function, but we have all the constraints are of the type less than or equal. So let's look at another classic problem, which has been studied in many variations of it. It's been studied in the online literature, and that's has more than one name. One of them is virtual circuit routing, and we're given a graph, and we have a bunch of requests. Each request specifies a source, a destination, and we need to route 1 unit of flow from SI to TI. Every edge has a capacity, and we don't want to exceed the capacity of the edges. So if edge E has capacity CE, it means that no more than C of E paths are allowed to be routed through that edge. And we want to maximize the total throughput, which is the number of requests that we're going to accept. We're not necessarily capable of accepting all requests. It's very easy to write this as an LP. The variable YRIP just says that is equal to 1 if request I can be routed on path P, and for every request we can only serve it once. So the sum of the over all possible paths for request Ri is less than or equal to 1. This means only one path per request. Maybe there's a pair SITI where a lot of flow can be routed. I want to avoid this situation. And for every edge, the total amount of the Y's of the paths and requests that go through that edge shouldn't be more than U of E. This is the capacity constraint. Okay, so just to be consistent, since this is a packing problem, I'm still going to call it the dual problem, even though this is our primary interest. So this is the LP that we just saw. What is the primal problem? So in the primal problem, we have a length x of E for every edge. And now, for every request, for every path, the length of the path has to be at least 1. Now, there are two ways of achieving that. So, XE is the length of edge E. So, either the sum of the XE's over the path is at least 1, or the path can ask for help from a variable Z of Ri, and Z of Ri is a variable which is specific to path I, and together they should be at least 1 for every path. And as before, since we're thinking of this as a dual problem, so now the columns arrive one by one. We have to decide immediately whether we accept or reject the request. And as before, we can only increase the variables. Okay, so the algorithm is going to be very similar to what we saw in the ski problem. So for every request, we're going to given request Ri, we're going to check whether one of its feasible paths has length strictly less than 1 with respect to the x length of the edges. If all of them have length at least 1, this means that the nth pair, SI-TI, is already feasible because all the paths connecting SI to TI have length 1, at least 1. So we only care about this request. It's going to help us if at least one of the paths connecting SI to TI has length strictly less than 1. In that case, we're going to pick just arbitrarily one of these paths. We're going to set z of Ri to be equal to 1 to make sure that all the paths of connecting SI to TI have length 1. And as before, this is the edges since we're now using the edges of this path, we're going to increase by a little bit the length of these edges by this multiplicative function. And we're going to set y on that path to be equal to 1, which means we're going to set a unit of flow on that path. So this is the complete algorithm. Analysis is similar to what we saw before. We need to show feasibility of primal and dual, and we need to bound the ratio of the primal, the ratio between the primal growth and the dual growth. Primal solution is feasible, just by definition. We made sure that this is going to happen. What about the ratio between the primal and dual? I'll just quickly go over it. So z is always set to be equal to. So if we accept the request, then y is equal to 1. So we have increased the dual by 1. What about the primals? And the primal, we set z to be equal to 1, and we multiply all the edges by this value. And then I won't go into the calculation, but it's straightforward that delta p, but by doing that, is actually bounded by at most 3. So we get the ratio of 3 to 1 between the primal and the dual increase. Now all we need to worry about is dual feasibility. So we're going to show, so actually we don't have dual feasibility, we're going to exceed the capacity, but we're not going to exceed the capacity by more than a logarithmic factor, and we'll show that by proving that for every edge, after we route this many paths through an edge, the length of the edge, x of e is at least 1. Once the length of an edge hits 1, we're not going to use that edge anymore because any path that goes through that edge already has length 1 with respect to the x values. So we won't push any more flow through that edge. The proof is, again, similar to what you saw in the C problem. The x variables induce a geometric sequence. So we have to see what is the value of x after u of e log n iterations, and that turns out, when you do the calculation, that turns out to be 1. So we've seen two examples, a covering problem and a packing problem. What happens here in general? So So let's see what is the key idea here. So let's say we have some primal problem, and we want to minimize sigma Cixi, and at the tth step we get a new constraint a1x1 up to and so on, which has to be greater than bt. And in the dual, we're going to get y. This is the contribution of variable yt to the dual objective function. So the question is, let's say we decide to increase yt additively by 1. What should be the value of, what should be the change in xi? So we want to make a connection between the change in primal cost, which is sigma ci times delta xi, and bt. So we've already decided to increase yt by 1, so which means that the dual has increased by bt. So we want to make a connection between the primal cost and the dual cost. And this is very simple. We know when the new constraint arrives, we can assume that it's not satisfied, because if it is satisfied, then there's nothing to be done. So we know that sigma aixi is at most bt. So now, just a simple calculation, we can set delta xi to be equal to aixi over ci. This is exactly what we did, or very similar to what we did before. The increase in xi was proportionally inverse to the cost of the variable xi in the objective function. But it's more than that. What does it mean that delta xi is proportional to aixi over ci? It means that the dx over dy is proportional to x, or in other words, the function that has this property is the exponential function. But this is really what we've been doing all the way in these previous two algorithms. So our multiplicative update rule was 1 plus 1 over c, but that's basically exponential in 1 over c, as long as c is not too small. So this actually gives us two ways of describing an online primal dual algorithm. We can do it, let's call it, this is the discrete way. Usually the description of the algorithm is simpler. Or we can do it using an exponential function. We can call this a continuous algorithm, and usually the analysis becomes simpler. Another way of thinking, so there's been all this line of work in the offline case of the multiplicative updates. I mean, the roots go back to work on multi-commodity flow by Matula and Shahroki, and I mean, there's a really long line of work. So one way of thinking about these ideas is that this is really the online, those works were in the offline case, and this is the online version of these works. 10 minutes? Okay. So let me skip. I thought I'd show you. I'll talk about the online set cover, because this is really where the roots of these ideas come from. But I'll skip this. Let me go to the paging problem. So paging problem is one of the first problems studied in the context of competitive analysis. It's a very basic problem in computer systems. We have some big universe of n pages. We have a cache which has room for k pages, And at every point, each time we get a request for a page. If that page is already in the cache, we're happy, we don't have to pay anything. Otherwise, we have to load the page into the cache, pay 1 unit, and the decision that we have to make is which page are we going to evict. And of course, we want to minimize the number of cache misses. It's well known, this is already in the original Slater-Tarjan paper, that every online algorithm is at least competitive, and LRU, least recently used, one of the classic algorithms actually used in practice, that's what we say, is that algorithm is K-competitive. As for randomized algorithm, there's again a classic paper which defined an algorithm called randomized marking. I won't go into the details, and that has an exponential improvement over the deterministic case, and it achieves a competitive factor of log K. Now, let's change the setting by a little bit, and suppose the loading cost is not uniform. So pages may come from various sources. It's not just a small computer, it may be a network. And now there's a fixed loading cost for every page, and now we want to minimize the total cost of loading the pages. Again, an upper bound of K is known, but the randomized competitiveness was completely open. The only known result was for the case of when instead of one weight function, like in the uniform case, we have the weights are one of two numbers. And in that case, it was a paper by Sandy Irani, which achieved log K, but otherwise no little o of K bound was known. And I mean, paging is a problem which is interesting on its own, but it's a very special case of the K-server problem, the holy grail problem in competitive analysis, where we're given a metric space, and we have K-servers, which are located somewhere in the metric space. We get requests. Every request is to a point in the metric space. And the way we serve a request is by sending one of the servers to the request point, and we have to pay the distance that the server travels in order to serve the request. Now, what's the relationship between paging and K-server? So K-server, so the uniform K-server is just K-server on a uniform metric, and we can think the pages which are in the cache, so the n pages correspond to the points in the metric. It's a uniform metric, and the K pages which are currently in the cache correspond to the points in the metric on which the servers are. Each time, if the page is in the cache, then we have to, then we don't have to, the server is there, we don't have to move it. Otherwise, we have to move a server from a page which is in the cache to the current page and pay 1 unit. So for general metrics, so this problem was open for a while, and there were several improvements. The difficulty is finding a competitive algorithm where the competitiveness is only a function of K, and following a sequence of results, the current best for a general metric space is 2K minus 1, and of course the lower bound is K. For trees and path trees, there is a simple K-competitive algorithm. But the randomized problem is completely open can we get a little O of k? This was not even known for weighted paging. If you think for a second, weighted paging corresponds to a metric space which is a weighted star, where the weight of a spoke in the star is equal to the loading cost of the page. So let's see how we can cast paging in our framework. So now pages are going to, we're going to keep fractions of pages in the cache, and these fractions should not add up to more than k. And if we have page I, loading cost of pi, we want to load epsilon of it into the cache, then we're going to pay epsilon times wi, the cost of page I. So the log k competitive algorithm is going to be done into, like in many of the previous algorithms, it's done in two steps. First, we're going to get a deterministic fractional algorithm, which is log k competitive. And then we'll do randomized rounding. It's not so simple like in the ski problem. And we'll do the randomized rounding step is also done online. So I'm going to concentrate only on the first part of getting the log k deterministic competitiveness for the fractional version. So first of all, let's set up the linear program, and remember we want to set it up as a covering problem. So let's look at page I. Suppose a request appeared. So this is the timeline, and a request appeared there, and then a request for page I appeared again right here. So we know that here the page had to be in the cache, and here it's again in the cache, and we can think of it as in between we have an interval indicating, corresponding to these two consecutive requests. So now we have intervals for many for all the pages that have appeared so far, and now we're looking at time point t, where page pt was requested, and let's call bt is just the current set of requests, the requests that are currently active, which is the set of intervals which cross point t. And we know that we can only keep k pages out of these, in the cache, out of these b of t pages, and page pt, the current request, has to be in the cache. And this means that from the remaining pages, bt minus pt, from the remaining set of active pages or active intervals, at least cardinality of bt minus k pages had to be evicted from the cache. How do we get an LP from this? So instead of loading, having variables indicating loading pages into the cache, we're going to charge for eviction, not for loading. And if you'll think about it for a second, charging for the difference between charging for eviction or charging for loading is just a constant which is independent of the request sequence. So the last time we load the pages is for free. We're not going to pay for it. So xij is the indicator variable for the event that page I is evicted from the cache between the jth request and the j plus first request. And for any point, at any point of time t, the constraint that we have is just what we verbally said before, that we have evicted at least this many pages, and the current request the x value, the x variable of the current request is set to 0. So 0 means that the page is in the cache, 1 means that the page is out of the cache. So at point t, the current page has to, its x variable has to be equal to 0. We have a dual problem. I don't want to go into the technical details. The important thing is that we have a variable yt, standing for time t, and we have a variable zij, which corresponds to page I and the jth time that it is requested. Now the algorithm, I'll describe it continuously, will take variable yt, dual variable yt, and will start increasing it continuously. So let's look at it graphically. So every page, let's look at variable xij, which denotes page I, jth time it is requested. So when it was requested, its value was set to 0 because it's in the cache. Question is when to evict it. So the rule is going to be, we start increasing variable y of t, and and then later on maybe time t plus 1, y of t plus 1, and so on. As long as the dual constraint corresponding to variable xij is not tight, the page is completely in the cache. Its value is 0. When the dual constraint becomes tight, then the value jumps to 1 over k. So in a way, this is reminiscent of the marking algorithm. In the marking algorithm, and as long as a page is marked, we're not going to, the probability that it is evicted is equal to 0. Only when all pages get marked and then unmarked, then the probability that the page is marked, page is evicted, is positive. So this region kind of corresponds to the case where the page is marked. Now when the dual becomes tight, or the complementary slackness condition is satisfied, then we start evicting. We start evicting a page slowly according to the exponential function that we saw before. And this goes on until xij hits 1, and then the page is completely out. So this region here corresponds to the situation where the page is unmarked. And once xij hits 1, then the page is fully evicted. I'm not going to go into the analysis, but the analysis has 2 parts. We'll show that the dual is violated by at most a log k factor, and the ratio between the primal and the dual is at most 2. And this implies that the algorithm is log k competitive. Just to say something about the analysis, show the log k competitive factor. In this region, it's similar to what we saw in the ski problem or in the virtual circuit routing. It just kind of follows from the fact that we're using an exponential function, and we get that this part pays log k. The more difficult part is showing that the jump, that we can justify the jump from 0 to 1 over k. Now, had we jumped from 0 to 1 over n, then that's easy to justify, and then the algorithm would have been log n competitive. But to get it, to justify from 0 to 1 over k, that requires a bit more work, and we show that the cost of each of these parts is upper bounded by the dual, and each part is done separately. And this gives a log k competitive algorithm for the fractional version, and then some more work is needed to take the fractional solution and online do randomized rounding. I'll stop at this point. I mean, there are several obvious questions, more applications, going beyond packing, covering. One extension which is easy and we know how to do it is have upper bounds on the variables, and we know a few more extensions, but something which is more general. And of course, going from weighted paging to the K-server problem is also a natural open problem. So, thank you.
אוקיי, אז תודה לכולם שנשארתם להבין. אני הולך לדבר על בניות מפורשות. I'm sleeping. Okay, I'm going to speak about the physical construction of epsilon nets for linear partial functions. So I will start with a motivating. No, it's not working. Okay, I will start with a natural question. We want to distribute point on the unit sphere in Rn that will look roughly random. Now, what do we mean by random? We can think about several notions of randomness, and we will focus on one of them. For example, we may wish that every small cup of the sphere will eat correctly, in the sense that the fraction of the points that will fall in the sphere roughly equals the weight of the sphere, or the measure of the sphere under the uniform measure. Another measure of randomness is that the points are not too concentrated in small cups. The different one is that we just want to eat every large cup. So let me just draw some picture. So we want to distribute points on the sphere. And now what is a cup? A cup means that we intersect the sphere with some hyperspace and take, say, one of the sides of this of the cup. Okay, so this is a cup. And what we want is the points to be distributed in some random sense with respect to spheres. So in this talk, we will focus on the third point. We just want to eat every large cup. In the sense that if this cup is not too small, if the weight is at least some epsilon, then we want at least one of the points to lie in this cup. Okay, so this is what we'll focus on. And, okay, but let me first state this question in the Boolean setting. Okay, so what I described now is the setting inside R to the n, and I want to describe the analog question for the Boolean Q. Okay, so what is a linear threshold function? A linear threshold function is a function that looks that has two parameters. It has a vector, a real vector A, and a parameter theta. And we say that f of x is 1 if the inner product of x with A is at least 2. Okay? So we all know threshold functions, and some well-known examples are the following. So think about theta as being 0, so the majority function is defined by the vector A of all ones. Right? If you have more ones and minus ones, then the sum will be positive. Similarly, we have sign majorities, where A is some arbitrary vector in the Boolean cube, or dictatorship, where A is this vector. Okay, so many functions can be described as linear threshold functions. And of course, these functions have many applications in computer science. I will not go into it, but they appear a lot in learning theory, in complexity theory, and they're very, very interesting. Okay, so we want. Okay, so by the way, what is the connection between linear threshold functions to the picture that we saw earlier? Then hyperspace is can be defined by its normal vector, and its normal vector can be thought of as being this A. So this condition just means that X lies above some or belongs to some half space. Okay. Now we want to construct epsilon nets. So what are epsilon nets? So an epsilon net, to define epsilon nets, we need the following scenario. We have some set omega, which is the world. It can be either the unit sphere or the Boolean cube. And we have a family of subsets. Let's call it R. Now an epsilon net is some subset of the world, okay? Some subset of omega, that has the following property. If we take a set from R, so think about R as a collection of sets. For example, think of if we take omega to be the sphere, then R can be the collection of all the cups in the sphere. Okay? So we want that for every set in R, for example, for every cup, if the measure of A, or the size of A, or some weight of A under some measure is large, and if A is not too small, then you want E to intersect A. Okay? So an epsilon net is a set of points that hit every large set in R. Okay, this is epsilon net. Okay. So there are many, so epsilon nets were studied a lot, and there are many theorems, and in particular this one showing that if the set R is not, okay, I don't want to get into what VC dimension is, but if the set R is not too large or too rich, then it is, then good epsilon nets exist in the sense that not too large epsilon nets exist. So if the VC dimension of R, and I don't want to get into definition, is small, is some number D, and you can think about D as, okay, as being a big parameter, then there is an epsilon net of size roughly linear in D, or linear in D over epsilon. Okay, and for those who know this notion, I mean, this dimension of linear threshold functions or all the objects that we are going to discuss, and of course, polynomial linear. Okay, so there are several scenarios for which epsilon nets were constructed. For example, for again, I don't want to get into it, but if you think about omega as Boolean cube, and R is the set of linear subspaces modulo 2. Okay, so R will be the set of linear spaces modulo 2, and the size is just the size of the subspace. Then we have an epsilon net for this set, which is just an epsilon biased space. This is actually more than an epsilon net, but call it an epsilon. Another family of objects for which epsilon nets are known are combinatorial rectangles. And this is by, so the first construction is by Nor, and the second one is by linear Luby substance. Okay, so epsilon nets are known in several scenarios. What we want to talk about today is epsilon nets for linear threshold functions. So here, so let us describe it over the Boolean cube. Here the world is the Boolean cube, and I'm going to think about the Boolean cube as being +1 and -1, okay, because it's going to be simple to speak about it this way. And the family of subsets is just going to be the set. I mean, you're going to look for each linear threshold function, you're going to look at its set of accepting inputs. Okay, so we're going to consider all subsets of the Boolean cube that are the accepting inputs of some linear threshold function. Okay, this is going to be the set. This is going to be our set system. Okay. Alternatively, if you can define R in a different way and just think about taking half space, so every set in R is just the intersection of the Boolean cube with some hyperspace. Right? We said that linear threshold functions can view them in two different ways. Okay, so we want to construct epsilon nets for this family. So this is the problem, and we want the epsilon net to be small, and we want it to be polynomial in n over epsilon. And it's not hard to see either by the previous theorem or by just picking some random subset of this size that such epsilon nets exist. Okay, so again, so what do we want? We want to find a set E, a subset of the Boolean cube, that is not too large, and such that if you give me a linear threshold function that accepts at least a function epsilon of the inputs, then there will be some point in E that F also accepts. So this is another question that we will look at is epsilon net for spherical cups. So previously you just considered the discrete domain, right? You just considered the Boolean cube. Now we will consider spherical cups. So here the world is the unit sphere in R to the n, and the measure is the uniform measure, and R is a set of all spherical cups. So again, this is the analog of the previous set system, because again, a spherical cup is the intersection of a sphere with a half space. Okay? Good. So again, so this is the problem, and it's exactly the same problem. Construct epsilon nets of size poly n over epsilon. And again, what we want to do is distribute points on the sphere that will fall into every large cut. And large is at least epsilon. Okay, so what is the motivation? So first of all, I think that this is a very natural problem. Geometrically, and just distributing points, if you look nice on the sphere, I think it's something that okay, we should all do. I mean, I encourage you to go home and tell this problem to your kids, but I think it's a very nice and natural question. But our motivation was actually to look, try to look for explicit constructions for other geometrical goals, or other geometrical functions. For example, our motivation was to try to do the Johnson-Wigner-Strauss dimension reductions deterministically. So what we did is basically was the first step towards this goal. I mean, it's a very preliminary step. But this was the main motivation. But other geometrical function that one may try to construct explicitly is to do compressed sensing via the restricted isometry property. I don't want to define it. This is again a very natural question of trying to construct a set of vectors on the unit field that have some property. And another geometrical question that we have randomized algorithm for, but we don't know how to do explicitly in polynomial time, is to find linear sections of L2 inside L1. So all of these, I don't want to define, are very natural geometrical questions, and we think that, constructing them explicitly is a very interesting approach. Okay, so I said that what we did was kind of first step towards this goal, and the idea was that, I mentioned before that epsilon bias subspaces are epsilon nets for some set system, and they will actually use this in order to fool or higher degree polynomials. And somehow it seems that in order to do this, the Johnson-Wigner-Strauss, we have to fight not only, not only cups, but rather some ellipsoids intersecting the sphere, something like this. So you want to fight, like, instead of linear threshold functions, some degree 2 threshold functions. So we were hoping that our construction would be a first step towards doing things for threshold functions of higher degree. So, okay, this is some vague motivation, but that's what we had. Okay, good. So I hope that you understand the problem, and the motivation we can agree or not, but at least the problem is well defined. And let me now describe our results. So basically we solved the problem of epsilon nets, both for the Boolean cube and for the sphere. So for the Boolean cube, we managed to construct a subset of size n to the epsilon, polynomial n to the epsilon, we'll see some universal constant independent of n and an epsilon. That is an epsilon. Okay, so this completely, okay, so up to the value of c, this is tight. You need at least n over epsilon and some polynomial, and manage to do it with some polynomial. I will not mention c. C can be improved, just hint. Maybe even cut several zeros, but don't. No, just yeah, but it's randomized. It's randomized. I give it to you. Okay. Another result is that we also, it's actually using this construction, we were also able to construct an epsilon for the spherical cups. I'll show it later, but basically what you take is, you take the construction for the cube, rotate it, and take the union of two things, and this gives an epsilon for the spherical cups as well. Okay, and I will just mention one corollary, which is the following. It seems quite complicated. Let me say what it says. A corollary of this theorem is the following. We can find a set of points inside the Boolean cube, E, which is not too large. Okay, so there is some universal constant C such that blah, 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 so E is not too large. And it has the following property that every point in the Boolean cube, every x, is not too far from our set E. So set E gives a covering code of the Boolean cube. So it's a polynomial size set, and for every point in the Boolean cube, there is some point in E that is not, it's not too far from it. It's the distance is most n over 2 minus log n times n. Okay? So this gives such sets are called covering codes, and So coupling codes were known before, but for example, dual BCH were, I think the most well-known code, coupling code. But if you want to achieve such parameters, then you need a set of size n to the log n. So in the previous this construction, there was no explicit construction of cover code of polynomial size that achieved this parameter. And I just want to mention that this corollary was also obtained by Noga. But, it's unpublished, right? Yeah, good. So history will not remember this, of course. No, it's not good in that sense. Another sense. Okay, anyway.
You just made sure it's a history which remember.
No, the video is not working. Okay, good. So I will start by explaining this result, and then just, I mean, this is an immediate corollary, so we can take it as an exercise. Fun saying it. And I'll try also, and then I'll explain why theorem 2 is a corollary of theorem 1. Okay, so the construction, so I will first consider, okay, so I want to do it for every linear threshold function, but let me first describe a construction that works for linear threshold functions where the vector A is only plus 1 or minus 1. So generally, A can be any vector. And I will now explain what to do in the case that all the coordinates of A are either 1 or minus 1. Okay, and I will also think about epsilon of mean 1 or polynomial. Okay, this is the range of parameters that we were interested in. Okay, so I will now just describe the construction. It will be 4 bullets, and then I will make some animation that. Okay, that's why I used PowerPoint as Noga said. Okay, so let K be some constant times log n. Okay, fix K to be log n. Now, what you want to do is you want to take a 4-ways independent sample space that lives inside a Boolean cube of length of dimension n over K. So, what is a 4-ways independent sample space? Sorry. It's a set of vectors that if you restrict your attention to only any 4 coordinates, then when you look at your set, then the values of these 4 coordinates are uniformly distributed. Okay, so you have a set of polynomially many vectors. It's polynomially n over k, and such that any 4 coordinates are uniformly distributed. Okay, so these are this is the basic ingredient. So such constructions are known and of size poly n over k. Okay. Now, what we're going to do, we're going to think about the element of S as vertices of an expander graph, a constant degree expander graph. Okay? So we have some expander graph whose vertices are the elements of S. Now, from all these ingredients, I now want to construct the set E. So what is the set E? The set E is living inside the n-dimensional Boolean cube. So I want to describe to you how I construct vectors in the Boolean cube. So what I do is that we consider all random walks, or all walks of length k minus 1 on this graph G. So what is a walk? We start from a vertex, we go to a neighbor of the neighbor, a neighbor of the neighbor, etc. for k minus 1 steps. So for each such walk, we get k vertices, right? The initial vertex plus the k minus 1 other vertices. And for every such walk, we just concatenate all the vertices that we saw on the way. So we call each element of S lives in n over k, is of length n over k. So if we concatenate k such things, we get a vector of length n. So let me give some animation, which will be the highlight of this talk. Okay, so we take a 4-ways independent sample space. And it has m points, or m is some polynomial. Now, we want to think about it as the node of the graph and take a random walk. So instead, let me just duplicate this k times. And now, so we have k duplicates of S. Okay, now we want to construct a vector of length n. So what we do is we pick a random vertex, or for every walk, right? So we start from a vertex, and then take a walk of length k. Okay, so we think about this walk as looking like this. And what we do eventually is we just concatenate the elements of the random walk to get a point in E. We do it for every initial vertex and for every walk from this vertex. Okay, so this is the construction. And in fact, just a side remark, for the case of uniform projection, for the case that A is only +1 and -1, a much simpler construction is possible, but this actually will be the construction that we will also use in a more general case, so I'm presenting it here. Okay, so this is the construction. So why does it work? So remember, we have A, which is +1 and -1, we have some theta, and we want to eat beyond epsilon, which is all over poly n. Now, what do I mean by this? I want to say, so we want the set E to contain an accepting input for every linear threshold function, where A is inside the Boolean cube, such that the probability that F accepts is at least 1 over polynomial. So I just want to understand what kind of thetas do we have to fight. So when does F accept? F accepts when A in a product with X is at least theta. So what kind of theta are possible if you want the acceptance probability to be at least 1 over polynomial? So it is not hard to see that, well, the set of accepting inputs are basically M in bold inside the Boolean cube, and that balls of this kind of values have measured 1 over polynomial in M. So this is just a simple Chernoff bound. Again, you can do the calculations. It's very simple. This is exactly Chernoff for the Boolean cube. And so basically, we want to prove that our set E contains some X that will have that such that the inner product of X with A will be at least this large. Okay, so this is what we have to prove. In order to show that our construction works, we have to prove that for every A inside the Boolean cube, or for every A which is +1, -1, that all the coordinates are +1, -1, there exists some element in our set that has inner product larger than this number. So this is what we're going to show. So given A, let's partition it. So we recall our construction was a concatenation of K vectors. So given a vector A, let's partition it to K parts, each of length another K. Now what do we want to show? We want to show that actually there exists some random walk S1 to Sk, such that the inner product of this guy with A is larger than m square root of n times log. So in order to show it, we will basically show that there exists some random walk such that the inner product of, so the ith part, the ith vertex of the walk and the ith part of A have large inner product for every I. Okay, so S1 is large inner product with A1, S2 is large inner product with A2, etc. And so when you sum over all the K products, you get large inner product. So this is what we are going to show. Okay, so recall that each element of E is a concatenation of K elements. We think about A also as a concatenation of K elements, and just going to show that point-wise, Si and Ai have large inner product, so overall the inner product is K times this number, which is square root of n times K, and this is exactly square root of n log n. Okay, so where did Si come from? So Si was an element of a 4-wise independent sample space. And it was shown long ago by Berger that if Ai is some +1 -1 vector and S is a 4-wise independent sample space, then a constant function of the element of S is large inner product with A. Okay? This is called a fourth moment method, but again, it's a simple calculation. Okay, what did you say? We said that, okay, we know that at the ith coordinate, a constant function, say 1/10 of all the elements of S is large inner product. But we want our random walk to eat each one of these small sets. And usually when we think about expander walks, we want to say that they escape every small set. But there is the less used direction of expander walks that says that if the expander is good enough and the sets are not too small, say a constant function, then you can actually, there is some walk that eats all these small sets. So, yes, so this A, okay, you know what A is, F is Urifege, so it's a long fege of Vigzrun and Zuckerman. Okay, so there will be some walk that will fall into each one of these subsets of S. Now what does it mean? It means that for this random walk, the inner product of S1 and A1 will be larger than this number. The inner product of A2 with S2 will be larger, etc. So overall, you're going to get what you want. So this is the complete proof for the case that A is a plus one minus one vector. Okay, so let's try to generalize it. Okay, how much time do I have? 30 minutes or 20 minutes? 25. Okay, 20 minutes. It costs me more. Okay. Okay, so what is the general case? So in the general case, A is not necessarily uniform. It means that some of the coordinates may be 0, some may be large, some may be small. It can have a few heavy coordinates, etc. So, first of all, previously it was very easy to understand what is the connection between epsilon and theta, right? We wanted epsilon to be one over polynomial, so we knew that theta had to be square root n log n. Now when A is not uniform, things change. It's not the same. For example, think about A as being the vector 1 and all zeros. So the inner product with every cube element is either 1 or minus 1. So you can never get inner product above 2, for example, right? So so we cannot just use theta as before. Okay, we have to understand the dependency of theta on A. This is one thing. Further, previously we partitioned A to k subsets in some predetermined way, right? The first n over k elements, the second set of n over k elements, etc. Now, it can be the case, for example, the case that I described, that all the weight of A will fall into just one of these subsets. Okay, and we somehow wanted to gain from every, right? The previous construction gained from, we had the inner product n over k, square root of n over k in each of these subsets, and then we sum. So we gain something from each of these partitions. Here we cannot guarantee it anymore. And finally, even if we do manage to have the weight of A to not be concentrated on one subset, we don't know that it is spread evenly among all the sets in the partition. Okay, so there are several problems when A is not uniform. Okay. So what we will do is first we will try to understand the dependence of theta on A and epsilon. And we will not work with a single partition, but we will work with a family of partitions. And we will try to get enough weight on many sets of the partition. Okay? It's not like before that the weight of A will be distributed evenly among all the k subsets, but we just will basically do what we can. We'll spread enough weight on many cells, if we will be able, if it's possible. Okay, so let me first try to explain what is the dependence of theta on A and epsilon. Okay. Good. So again, we want to understand, given A and epsilon, what is the theta such that this happens. Whenever this happens, we know that it's enough to get inner product above theta and to be done with. Okay, and I will not show the proof, but this is what we do, what we take. Let I be the set of large coordinates of A. So if epsilon is polynomially small, then I is the set of size O of log N. So let I be the set of largest log N coordinates of A. And largest, I mean by absolute value. Okay? So I claim that theta that satisfies this is roughly this number. Now what does it say? Here we take the sum of absolute values of the coordinates inside I. Okay, A subscript I means just the vector A restricted to set I. So theta will be the sum of the largest O of log 1, say log n, the largest log n coordinates of A, plus an element that looks like what we had earlier. Here it will be, so let's go back to the previous case. So A was plus 1 or minus 1. So here we don't have large coordinates. Okay, so let's just forget about it. All the coordinates are the same. What we have here, this is square root of n, this is square root of log n. Okay, so when A is uniform, this is the only element that matters. When A is not uniform, we also need to take into account the sum of the largest log n coordinates of A. Okay, this is theta. And this is it's quite easy to prove this boundary. So our goal now will be to somehow get inner product larger than this thing. So somehow we will have to both catch the correct sign on the largest element of A and get enough weight from the others. Okay, so this will be our goal. Now, what kind of partition is needed? We said that one partition is not enough, right? Because all the weight can be concentrated on one subset. So, one thing that we would like for our partition to satisfy is that all the heavy coordinates of A fall into different buckets or into different subsets in the partition. Okay? So previously A was uniform, so all the coordinates were equally important. Other way of saying it is that there were no heavy coordinates. Here we want heavy coordinates. We don't want two heavy coordinates to be in the same subset. Okay, this is one thing that we want. And the second thing that we want is that after we distribute the heavy coordinates, we want the rest of the weight, if anything is left, to be, well, roughly equally distributed. And when I say roughly equally distributed, I mean that a large fraction of the remaining weight will be evenly distributed on enough subsets. Okay? So just, I mean, I don't want to get into parameters, but we want all the heavy elements to be in different subsets, and the weight to be distributed almost evenly on many subsets. Okay. Good. So for example, when A is just a vector 1 and all zeros, there is nothing to do because every partition will satisfy it, right? I mean, there's only one heavy coordinate, it will fall into one cell. And the interesting case is where A is polylog many coordinates, so we want the largest of them, I mean the largest log n coordinates to fall into different subsets, and the other polylog to somehow be distributed roughly evenly. That's, I mean, some case that you can remember if you want to understand what you're doing. Okay, so, okay, I don't want to, it's late, so let's just say what there exists. So, Noga mentioned this result earlier. So, now I want to say what kind of partitions do we take. So the partitions that we take come from a family of what we call perfect hash functions. And the short story is the following. There exists a small family of mappings, and this family is very explicit, such that the following happens. If A is not too concentrated, meaning that it has, say, more than log n coordinates or something like this, then there exists some mapping in our family H that maps, okay, so H maps the set of n elements, think about it as some order log n elements. Okay, take a family of mappings from n elements to log n elements. And our mapping is basically the way that we partition the coordinates into subsets. Okay, the elements that fall into the first subset will be mapped to 1, the elements that fall into the second subset will be mapped to 2, etc. Okay, so every partition is basically a function from n to log n coordinates. And the family H satisfies that if A is not too concentrated, then there exists some function, or basically some partition, that is both one-to-one on the element of A. So it sends it to different subsets, and the rest of the weight of A is distributed roughly evenly on many other subsets. So this is not what, so Schmidt and Siegel gave the first explicit construction of such a family. Of course, there were other constructions, but they were the first to give a non-adaptive construction, right? A family of hash functions. And they, of course, did not consider, they only consider the first thing, to be one-on-one on a small set, right? To hash a small set of elements in a one-to-one way. And by taking their construction, just walking with it a little bit, you see that it also satisfies the second way. Okay, so there exists a small set of partitions that will have the required property. Okay, that it's one-to-one with every element of A, and most of the other weight, most of the remaining weight is distributed roughly evenly. Okay. So what do we do now? So, I mean, I claim that this is what we need in order to at least to make the idea feasible, but this is actually enough. Let's see the construction. Okay, you know, I'll skip this. It's again nice animation, but let's skip the hash functions. Okay, So let's go to the construction of for general A. And of course, if you'll beg at the end of the talk, I will go back to the slides, but it's up to you. Okay, so again, let S be some log n. As I said, every age, every family in H defines a partition, right? In the same way that I described earlier. So let's fix such a partition, okay? Now, okay, so now instead of using a 4-wise independent set, we are going to use a 5-wise independent set. So this is the fifth moment method. And I can think about other generalizations, but it's too wild to state it here. Okay, so this is the 5-wise method, okay? So take the 5-wise independent sample space, S. And let's not worry about the length now, because one small point is that H may partition this A to sets that are not of equal size. Okay, so let's assume that S is minus 1 amount to the n. Okay? Again, it's polynomial. And as before, we're going to construct an expander whose nodes are the elements of S. Take a random walk. So we call the family H mapped n elements to 10 S elements. So we take 10 S minus 1 random walk, and then we concatenate all the elements to get 1 point. Okay, so it's exactly the construction as before. The only thing that we have to be careful is that because the subsets are of different length, we just S is of length n. So whenever a set is of length, say n over 2, we just take the first n over 2 bits of the element of S, so that the overall concatenated vector will have length n. So, okay, don't worry about it. Basically, it's the same construction as before, and just some nuances. Okay, so why does it work? What's the intuition? Okay, I will not go into calculations. The intuition is the following. So, we call it H is 1-to-1 on the heavy elements of A. So, the heavy elements of A fall into different cells. Now, what we're going to do is, we have a 5-wise independent sample space. So we're going to sacrifice 1 degree of independence and fix the sign of the every coordinate in each cell. Okay, what does it mean to be 5-wise independent? It means that every 5 coordinates are uniformly distributed. Okay, so now just imagine that the every coordinate of A fell into the first cell, and it's the first element there. Then in the set S, half of the set S will be elements that have +1 on the first coordinate. So we'll exactly catch the heavy element. So after fixing the sign of the heavy element, we are still left with 4-wise independence. So we can do it for every cell that contains an heavy element. So now we have caught actually the absolute value, the sum of the absolute values of the heavy elements, and we are left with a 4-wise independent sample space. Using it, you can just repeat the previous argument, and again, you have to be very careful, but because the H roughly distributed the weight of A equally between many cells, then we will get enough inner product from the remaining elements. Okay, so I don't want to get into details, but this is exactly what happens there. And, okay, if you trust me, you believe me. Otherwise, you can read the paper and look for bugs. Okay, so this is basically the proof. Okay. So let's move to a sphere. So as I promised, the construction for the sphere will just be a rotation of this construction. So first, let me explain why this construction does not work for spherical cups. So first of all, the Boolean cube is not a subset of the sphere, right? The sphere contains unit vectors, and the Boolean cube contains vectors with coordinates +1 and -1. So let's ignore it. Just normalize the Boolean cube to live inside the sphere. Okay, so now the Boolean cube is -1 over square root. Here it's a subset of the unit sphere. So a natural attempt will be to take the epsilon that we constructed and let it be the epsilon for spherical cups. But again, the problem is with this subspace, or linear regression function. Take A to be this vector, and take it to be this node. Now, what is the inner product of A with any element of the Boolean cube? So the Boolean cube is now +1 over square root n, -1 over square root n. So the inner product is either 1 over square root n or -1 over square root n. So we never pass this threshold. But again, by churn of pound, it's not easy, it's not difficult to show that if you take the cup, if you take this if you take the cup defined with these parameters, then its weight is polynomially large. So this set does not intersect this cup. But what is the problem? The problem is that A is very, very concentrated. It's concentrated only on one coordinate. So it turns out that the solution is to spread A. So, okay, so this is the problem. And now what we do to solve it is the following. Let F be the Fourier matrix. Okay, just assume that there is, that N is good enough. Up to factor 2 it's okay. So let F be the Fourier matrix, the normalized Fourier matrix. So every point is plus 1 or minus 1 over square root N, and it's a unitary matrix. Okay, F times F transpose is identical. So the set equivalent that we'll take will be E, union with F of E. So we'll take every point of E and rotate it with F, and take the union of these two sets. Now what is the idea? The idea is that if you look at, for any vector A, either A or F of A, so F is also equal to F transpose, so we can speak about what F does to A instead of what F does to E. So for every vector A, either A is well spread or F of A is well spread in some sense. Okay, I don't want to get into which sense. But once A is spread enough, then actually the previous construction also works for that A. And that's it. Okay, so again, I'm not going into details, but that's the whole idea. And so, so the only problem with this example was that A was very concentrated. So once you spread the weight of A on many coordinates, you get what you want. And what I mean spread is mean that a large fraction of the weight of A sits on coordinates that are small, namely the numbers. Okay, so this is what I'm going to say about this thing. And let's conclude. But still, you can beg for the previous slides. I'm willing to keep. Okay, so we constructed epsilon nets of size poly n over epsilon for linear attachment functions over the Boolean cube and over the sphere. But the motivating questions like the randomizing, like giving explicit dimension induction or constructing restricted geometry property, satisfied with RAP, etc., still open. Particularly, the following question is still open. For example, pseudo-random generators for linear attachment functions. So if you think about what we said, we just wanted to eat spherical cups. A pseudo-random generator will actually eat a spherical cup the correct number of times. So the fraction of points from E that will end in the cup is comparable to the weight of the cup, up to epsilon. Now, it's not too difficult to see. In fact, this was recently shown that if you take such sets, there are constructions of this size that actually do it for epsilon. This is polynomial only when epsilon is constant. When epsilon is polynomially small, this does not work. Okay, so this is it's basically take one of the square root epsilon independence or one of the epsilon square independence. I don't remember, and it works. Yeah, but it only works for a constant epsilon. That's, it's only good for a constant epsilon. And okay. And in particular, the following thing is open, at least for us. It's an open question around me. I'm not sure whether if you go a little bit further, it's still open. You want to construct a set. It's not too concentrated on small cups. So this is basically the opposite of what we did. We wanted to construct a set that hit every cup. Now I want to construct a set that is not too concentrated on cups. Okay, that in the sense that if you take a cup, which is I'm just consider it not concentrated on small cups. So I just want to construct a set that if you take a cup of weight 1 over polynomial in there, then it does not contain more than a polynomial large fraction of our set. I don't want that, 1 over log n of my set to sit in such small cups. Okay, so I just want to be pseudo-random for small cups. Okay, that's it. Thank you.